Dove Books on Tape presents Chaos by James Gleick. The police in the small town of Los Alamos, New Mexico, worried briefly in 1974 about a man seen prowling in the dark night after night, the red glow of his cigarette floating along the back streets. He would pace for hours, heading nowhere in the starlight that hammers down through the thin air of the mesas. The police were not the only ones to wonder. At the National Laboratory, some physicists had learned that their newest colleague was experimenting with 26-hour days, which meant that his waking schedule would slowly roll in and out of phase with theirs. This bordered on strange, even for the theoretical division. In the 3 decades since J. Robert Oppenheimer chose this unworldly New Mexico landscape for the atomic bomb project, Los Alamos National Laboratory had spread across an expanse of desolate plateau, bringing particle accelerators and gas lasers and chemical plants, thousands of scientists and administrators and technicians, as well as one of the world's greatest concentrations of supercomputers. Some of the oldest scientists remembered the wooden buildings rising hastily out of the rim rock in the 1940s, but to most of the Los Alamos staff, young men and women in college-style corduroys and work shirts, the first bomb makers were just ghosts. The laboratory's locus of purist thought was the theoretical division known as T division, just as computing was C division and weapons was X division. More than 100 physicists and mathematicians worked in T division, well paid and free of academic pressures to teach and publish. The scientists had experience with brilliance and with eccentricity. They were hard to surprise. But Mitchell Feigenbaum was an unusual case. He had exactly 1 published article to his name, and he was working on nothing that seemed to have any particular promise. His hair was a ragged mane sweeping back from his wide brow in the style of busts of German composers. His eyes were sudden and passionate. When he spoke, always rapidly, he tended to drop articles and pronouns in a vaguely Middle European way, even though he was a native of Brooklyn. When he worked obsessively. When he couldn't work, he walked and thought day or night, and night was best of all. The 24-hour day seemed too constraining. Nevertheless, his experiment in personal quasi-periodicity came to an end when he decided that he could no longer bear waking to the setting sun, as had to happen every few days. At the age of 29, he had already become an ad hoc consultant whom scientists would go to see about any especially intractable problem, when they could find him. One evening, he arrived at work just as the director of the laboratory, Harold Agnew, was leaving. Agnew was a powerful figure, one of the original Oppenheimer apprentices. He'd flown over Hiroshima on an instrument plane that accompanied the Enola Gay, photographing the delivery of the laboratory's first product. "I understand you're real smart," Agnew said to Feigenbaum. "If you're smart, why don't you just solve laser fusion?" To a physicist, creating laser fusion was a legitimate problem. Puzzling out the spin and color and flavor of small particles was a legitimate problem. Dating the origin of the universe was a legitimate problem. Understanding clouds was a problem for meteorologists. Like other physicists, Feigenbaum used an understated, tough guy vocabulary to rate such problems. Such a thing is obvious, he might say, meaning that a result could be understood by any skilled physicist after appropriate contemplation and calculation. Not obvious described work that commanded respect and Nobel Prizes. For the hardest problems, the problems that would not give way without long looks into the universe's bowels, physicists reserved words like deep. In 1974, though few of his colleagues knew it, Feigenbaum was working on a problem that was deep. Chaos. Where chaos begins, classical science stops. For as long as the world has had physicists inquiring into the laws of nature, it has suffered a special ignorance about disorder in the atmosphere, in the turbulent sea, in the fluctuations of wildlife populations, in the oscillations of the heart and the brain. The irregular side of nature, the discontinuous and erratic side, these have been puzzles to science. But in the 1970s, a few scientists in the United States and Europe began to find a way through disorder. They were mathematicians, physicists, biologists, chemists, all seeking connections between different kinds of irregularity. Physiologists found a surprising order in the chaos that develops in the human heart, the prime cause of sudden, unexplained death. Ecologists explored the rise and fall of gypsy moth populations. Economists dug out old stock price data and tried a new kind of analysis. The insights that emerged led directly into the natural world, the shapes of clouds, the paths of lightning, the microscopic intertwining of blood vessels, the galactic clustering of stars. When Mitchell Feigenbaum began thinking about chaos at Los Alamos, he was one of a handful of scattered scientists, mostly unknown to one another. A mathematician in Berkeley, California, had formed a small group dedicated to creating a new study of dynamical systems. A population biologist at Princeton University was about to publish an impassioned plea that all scientists should look at the surprisingly complex behavior lurking in some simple models. A geometer working for IBM was looking for a new word to describe a family of shapes, jagged, tangled, splintered, twisted, fractured, that he considered an organizing principle in nature. A French mathematical physicist had just made the disputation's claim that turbulence in fluids might have something to do with a bizarre, infinitely tangled abstraction that he called a strange attractor. A decade later, chaos has become a shorthand name for a fast-growing movement that is reshaping the fabric of the scientific establishment. Chaos conferences and chaos journals abound. At every major university and every major corporate research center, some theorists ally themselves first with chaos and only second with their nominal specialties. Chaos has created special techniques of using computers and special kinds of graphic images, pictures that capture a fantastic and delicate structure underlying complexity. The new science has spawned its own language, an elegant shop talk of fractals, bifurcations, intermittences, and periodicities, folded tau diffeomorphisms, and smooth noodle maps. These are the new elements of motion, just as in traditional physics, quarks and gluons are the new elements of matter. To some physicists, chaos is a science of process rather than state, of becoming rather than being. Now that science is looking, chaos seems to be everywhere. A rising column of cigarette smoke breaks into wild swirls. A flag snaps back and forth in the wind. A dripping faucet goes from a steady pattern to a random one. Chaos appears in the behavior of cars clustering on an expressway, the behavior of oil flowing in underground pipes. No matter what the medium, the behavior obeys the same newly discovered laws. That realization has begun to change the way business executives make decisions about insurance, the way astronomers look at the solar system, the way political theorists talk about the stresses leading to armed conflict. Chaos breaks across the lines that separate scientific disciplines. Because it is a science of the global nature of systems, it has brought together thinkers from fields that had been widely separated. The first chaos theorists, the scientists who set the discipline in motion, shared certain sensibilities. They had an eye for pattern, especially pattern that appeared on different scales at the same time. They had a taste for randomness and complexity, for jagged edges and sudden leaps. Believers in chaos speculate about determinism and free will, about evolution, about the nature of conscious intelligence. They feel that they are turning back a trend in science toward reductionism, the analysis of systems in terms of their constituent part, quarks, chromosomes, or neurons. They believe that they are looking for the whole. The most passionate advocates of the new science go so far as to say that 20th century science will be remembered for just three things: relativity, quantum mechanics, and chaos. Chaos, they contend, has become the century's third great revolution in the physical sciences. Like the first two revolutions, chaos cuts away at the tenets of Newton's physics. As one physicist put it, relativity eliminated the Newtonian illusion of absolute space and time. Quantum theory eliminated the Newtonian dream of a controllable measurement process. And chaos eliminates the Laplacian fantasy of deterministic predictability. Of the three, the revolution in chaos applies to the universe we see and touch, to objects at human scale. Everyday experience and real pictures of the world have become legitimate targets for inquiry. There's long been a feeling, not always expressed openly, that theoretical physics has strayed far from human intuition about the world. Whether this will prove to be fruitful heresy or just plain heresy, no one knows. But some of those who thought physics might be working its way into a corner now look to chaos as a way out. Within physics itself, the study of chaos emerged from a backwater. The mainstream for most of the 20th century has been particle physics, exploring the building blocks of matter at higher energies, smaller and smaller scales, shorter and shorter times. Out of particle physics have come theories about the fundamental forces of nature and about the origin of the universe. Yet, some young physicists have grown dissatisfied with the direction of the most prestigious of sciences. Progress has begun to seem slow, the naming of the new particles futile, the body of theory cluttered. With the coming of chaos, younger scientists believed that they were seeing the beginnings of a course change for all of physics. The field had been dominated long enough, they felt, by the glittering abstractions of high-energy particles and quantum mechanics. The cosmologist Stephen Hawking, occupant of Newton's chair at Cambridge University, spoke for most of physics when he took stock of his science in a 1980 lecture titled, "Is the End in Sight for Theoretical Physics?" We already know the physical laws that govern everything we experience in everyday life. It is a tribute to how far we've come in theoretical physics that it now takes enormous machines and a great deal of money to perform an experiment whose results we cannot predict. Yet, Hawking recognized that understanding nature's laws on the terms of particle physics left unanswered the question of how to apply those laws to any but the simplest of systems. Predictability is one thing in a cloud chamber where two particles collide at the end of a race around an accelerator. It is something else altogether in the simplest tub of roiling fluid, or in the Earth's weather, or in the human brain. Hawking's physics, efficiently gathering up Nobel Prizes and big money for experiments, has often been called a revolution. At times, it seemed within reach of that grail of science, the grand unified theory, or theory of everything. Physics had traced the development of energy and matter in all but the first eye blink of the universe's history. But was post-war particle physics a revolution? Or was it just the fleshing out of the framework laid down by Einstein, Bohr, and the other fathers of relativity and quantum mechanics? Certainly, the achievements of physics, from the atomic bomb to the transistor, changed the 20th century landscape. Yet, if anything, the scope of particle physics seemed to have narrowed. 2 generations had passed since the field produced a new theoretical idea that changed the way non-specialists understand the world. The physics described by Hawking could complete its mission without answering some of the most fundamental questions about nature. How does life begin? What is turbulence? Above all, in a universe ruled by entropy, drawing inexorably toward greater and greater disorder, how does order arise? At the same time, objects of everyday experience, like fluids and mechanical systems, came to seem so basic and so ordinary that physicists had a natural tendency to assume that they were well understood. It was not so. As the revolution in chaos runs its course, the best physicists find themselves returning without embarrassment to phenomena on a human scale. They study not just galaxies, but clouds. They carry out profitable computer research, not just on Crays, but on Macintoshes. The premier journals print articles on the strange dynamics of a ball bouncing on a table side by side with articles on quantum physics. The simplest systems are now seen to create extraordinarily difficult problems of predictability. Yet, order arises spontaneously in those systems, chaos and order together. Only a new kind of science could begin to cross the great gulf between knowledge of what one thing does, one water molecule, one cell of a heart tissue, one neuron, and what millions of them do. Watch 2 bits of foam flowing side by side at the bottom of a waterfall. What can you guess about how close they were at the top? Nothing. As far as standard physics was concerned, God might just as well have taken all those water molecules under the table and shuffled them personally. Traditionally, when physicists saw complex results, they looked for complex causes. When they saw a random relationship between what goes into a system and what comes out, they assumed that they would have to build randomness into any realistic theory by artificially adding noise or error. The modern study of chaos began with the creeping realization in the 1960s that quite simple mathematical equations could model systems every bit as violent as a waterfall. Tiny differences in input could quickly become overwhelming differences in output, a phenomenon given the name sensitive dependence on initial conditions. In weather, for example, this translates into what is only half-jokingly known as the butterfly effect, the notion that a butterfly stirring the air today in Peking can transform storm systems next month in New York. When the explorers of chaos began to think back on the genealogy of their new science, they found many intellectual trails from the past. But one stood out very clearly. For the young physicists and mathematicians leading the revolution, a starting point was the butterfly effect. The butterfly effect. The sun beat down through a sky that had never seen clouds. The wind swept across an earth as smooth as glass. Night never came, and autumn never gave way to winter. It never rained. The simulated weather in Edward Lorenz's new electronic computer changed slowly but certainly, drifting through a permanent dry midday season as if the world had turned into Camelot, or some particularly bland version of Southern California. Outside his window, Lorenz could watch real weather, the early morning fog creeping along the Massachusetts Institute of Technology campus, or the low clouds slipping over the rooftops from the Atlantic. Fog and clouds never arose in the model running on his computer. The machine, a Royal MacBee, was a thicket of wiring and vacuum tubes that occupied an ungainly part of Lorenz's office, made a surprising and irritating noise, and broke down every week or so. It had neither the speed nor the memory to manage a realistic simulation of the Earth's atmosphere and oceans. Yet Lorenz created a toy weather in 1960 that succeeded in mesmerizing his colleagues. Every minute the machine marked the passing of a day by printing a row of numbers across a page. If you knew how to read the printouts, you would see a prevailing westerly wind swing now to the north, now to the south, now back to the north. Digitized cyclones spun slowly around an idealized globe. As word spread through the department, the other meteorologists would gather around with the graduate students, making bets on what Lorenz's weather would do next. Somehow, nothing ever happened the same way twice. Lorenz enjoyed weather, by no means a prerequisite for a research meteorologist. He savored its changeability. He appreciated the patterns that come and go in the atmosphere, families of eddies and cyclones, always obeying mathematical rules, yet never repeating themselves. When he looked at clouds, he thought he saw a kind of structure in them. Once he had feared that studying the science of weather would be like prying a jack-in-the-box apart with a screwdriver. Now he wondered whether science would be able to penetrate the magic at all. Weather had a flavor that could not be expressed by talking about averages. The daily high temperature in Cambridge, Mass. averages 75 degrees in June. The number of rainy days in Riyadh, Saudi Arabia, averages 10 a year. These were statistics. The essence was the way patterns in the atmosphere changed over time. And that was what Lorenz captured in the Royal MacBee. To most serious meteorologists, forecasting was less than science. It was a seat-of-the-pants business performed by technicians who needed some intuitive ability to read the next day's weather in the instruments and the clouds. It was guesswork. At centers like MIT, meteorology favored problems that had solutions. Lorenz understood the messiness of weather prediction as well as anyone, but he harbored an interest in the problem, a mathematical interest. Not only did meteorologists scorn forecasting, but in the 1960s, virtually all serious scientists mistrusted computers. These souped-up calculators hardly seemed like tools for theoretical science, so numerical weather modeling was something of a bastard problem. Yet the time was right for it. Weather forecasting had been waiting 2 centuries for a machine that could repeat thousands of calculations over and over again by brute force. In theory, a computer could let meteorologists do what astronomers have been able to do with pencil and slide rule: reckon the future of their universe from its initial conditions and the physical laws that guide its evolution. The equations describing the motion of air and water were as well known as those describing the motion of planets. Astronomers did not achieve perfection and never would. Not in a solar system tugged by the gravities of 9 planets, scores of moons, and thousands of asteroids, but calculations of planetary motion were so accurate that people forgot that they were forecasts. When an astronomer said, "Comet Halley will be back this way in 76 years, it seemed like fact, not prophecy. Deterministic numerical forecasting figured accurate courses for spacecraft and missiles. Why not winds and clouds? There was always one small compromise, so small that working scientists usually forgot it was there, lurking in a corner of their philosophies like an unpaid bill. Measurements could never be perfect. With his primitive computer, Lorenz had boiled weather down to the barest skeleton. Yet, line by line, the winds and temperatures in Lorenz's printouts seemed to behave in a recognizable earthly way. They matched his cherished intuition about the weather, his sense that it repeated itself, displaying familiar patterns over time, pressure rising and falling, the air streams swinging north and south, but the repetitions were never quite exact. There was pattern with disturbances, an orderly disorder. To make the patterns plain to see, Lorenz created a primitive kind of graphics. Instead of just printing out the usual lines of digits, he would have the machine print a certain number of blank spaces, followed by the letter A. He would pick one variable, perhaps the direction of the airstream. Gradually, the A's marched down the roll of paper, swinging back and forth in a wavy line, making a long series of hills and valleys that represented the way the west wind would swing north and south across the continent. The orderliness of it, the recognizable cycles coming around again and again, but never twice the same way, had a hypnotic fascination. The system seemed slowly to be revealing its secrets to the forecaster's eye. One day in the winter of 1961, wanting to examine one sequence at greater length, Lorenz took a shortcut. Instead of starting the whole run over, he started midway through. To give the machine its initial conditions, he typed the numbers straight from the earlier printout. Then he walked down the hall to get away from the noise and drink a cup of coffee. When he returned an hour later, he saw something unexpected, something that planted a seed for a new science. This new run should have exactly duplicated the old. Lorenz had copied the numbers into the machine himself. The program had not changed. Yet, as he stared at the new printout, Lorenz saw his weather diverging so rapidly from the pattern of the last run that within just a few months, all resemblance had disappeared. He looked at one set of numbers, then back at the other. He might as well have chosen 2 random weathers out of a hat. His first thought was that another vacuum had gone bad. Suddenly he realized the truth. There'd been no malfunction. The problem lay in the number that he typed. In the computer's memory, 6 decimal places were stored, 0.506127. On the printout, to save space, just 3 appeared, 0.506. Lorenz had entered the shorter, rounded-off number, assuming that the difference, 1 part in 1,000, was inconsequential. He decided to look more closely at the way 2 nearly identical runs of weather flowed apart. He copied one of the wavy lines of output onto a transparency and laid it over the other to inspect the way it diverged. First, 2 humps matched detail for detail. Then one line began to lag a hair's breadth behind. By the time the 2 runs reached the next hump, they were distinctly out of phase. By the 3rd or 4th hump, all similarity had vanished. It was only a wobble from a clumsy computer. Lorenz could have assumed something was wrong with his particular machine or his particular model, probably should have assumed, but for reasons of mathematical intuition that his colleagues would begin to understand only later, Lorenz felt a jolt. Something was philosophically out of joint. The practical import could be staggering. Although his equations were gross parodies of the Earth's weather, he had a faith that they captured the essence of the real atmosphere. That first day, he decided that long-range weather forecasting must be doomed. The 50s and 60s were years of unreal optimism about weather forecasting. Newspapers and magazines were filled with hope for weather science, not just for prediction, but for modification and control. Two technologies were maturing together, the digital computer and the space satellite. An international program was being prepared to take advantage of them, the Global Atmosphere Research Program. There was an ideal that human society would free itself from weather's turmoil and become its master instead of its victim. Geodesic domes would cover cornfields, airplanes would seed the clouds, scientists would learn how to make rain and how to stop it. The intellectual father of this popular notion was John van Neumann, who built his first computer with the precise intention, among other things, of controlling the weather. He surrounded himself with meteorologists and gave breathtaking talks about his plans to the general physics community. He had a specific mathematical reason for his optimism. He recognized that a complicated dynamical system could have points of instability, critical points where a small push can have a large consequence, as with a ball balanced at the top of a hill. With the computer up and running, van Neumann imagined that scientists would calculate the equations of fluid motion for the next few days. Then a central committee of meteorologists would send up airplanes to lay down smoke screens or seed clouds to push the weather into the desired mode. But von Neumann had overlooked the possibility of chaos, with instability at every point. By the 1980s, a vast and expensive bureaucracy devoted itself to carrying out von Neumann's mission, or at least the prediction part of it. America's premier forecasters operated out of an unadorned cube of a building in suburban Maryland, near the Washington Beltway, with a spy's nest of radar and radio antennas on the roof. Their supercomputer ran a model that resembled Lorenz's only in its fundamental spirit. Where the Royal MacBee could carry out 60 multiplications each second, the speed of a control data Cyber 205 was measured in megaflops, millions of floating point operations per second. Where Lorenz had been happy with 12 equations, the modern global model calculated systems of 500,000 equations. The model understood the way moisture moved heat in and out of the air when it condensed and evaporated. The digital winds were shaped by digital mountain ranges. Data poured in hourly from every nation on the globe, from airplanes, satellites, and ships. The National Meteorological Center produced the world's second-best forecasts. The best came out of Reading, England, a small college town about an hour's drive from London. The European Center for Medium-Range Weather Forecasts occupied a modest tree-shaded building. It was built in the heyday of the all-European common market spirit, when most of the nations of Western Europe decided to pool their talent and resources in the cause of weather prediction. The Europeans attributed their success to their young rotating staff, no civil service, and their Cray supercomputer, which always seemed to be one model ahead of the American counterpart. Weather forecasting was the beginning, but hardly the end of the business of using computers to model complex systems. The same techniques served many kinds of physical scientists and social scientists, hoping to make predictions about everything from the small-scale fluid flows that concerned propeller designers to the vast financial flows that concerned economists. Indeed, by the 70s and 80s, economic forecasting by computer bore a real resemblance to global weather forecasting. The models were churned through complicated, somewhat arbitrary webs of equations meant to turn measurements of initial conditions, atmospheric pressure or money supply, into a simulation of future trends. The programmers hoped the results were not too grossly distorted by the many unavoidable simplifying assumptions. If a model did anything too obviously bizarre, flooded the Sahara or tripled interest rates, the programmers would revise the equations to bring the output back in line with expectation. In practice, econometric models proved dismally blind to what the future would bring, but many people who should have known better acted as though they believed in the results. Forecasters of economic growth or unemployment were put forward with an implied precision of 2 or 3 decimal places. Governments and financial institutions paid for such predictions and acted on them, perhaps out of necessity or for want of anything better. Presumably they knew that such variables as consumer optimism were not as nicely measurable as humidity, and that the perfect differential equations had not yet been written for the movement of politics and fashion. But few realized how fragile was the very process of modeling flows on computers, even when the data was reasonably trustworthy and the laws were purely physical, as in weather forecasting. Computer modeling had indeed succeeded in changing the weather business from an art to a science. The European Centre's assessment suggested that the world saved billions of dollars each year from predictions that were statistically better than nothing. But beyond 2 or 3 days, the world's best forecast was speculative, and beyond 6 or 7, they were worthless. The butterfly effect was the reason. For small pieces of weather, and to a global forecaster small can mean thunderstorms and blizzards, any prediction deteriorates rapidly. Errors and uncertainties multiply, cascading upward through a chain of turbulent features, from dust devils and squalls up to continent-sized eddies that only satellites can see. Even for experienced meteorologists, all this runs against intuition. One of Lorenz's oldest friends was Robert White, a fellow meteorologist at MIT, who later became head of the National Oceanic and Atmospheric Administration. Lorenz told him about the butterfly effect and what he felt it meant for long-range prediction. White gave Van Neumann's answer. "Prediction nothing," he said. "This is weather control." His thought was that small modifications, well within human capability, could cause desired large-scale changes. Lorenz saw it differently. Yes, you could change the weather, you could make it do something different from what it would otherwise have done, but if you did, then you would never know what it would otherwise have done. It would be like giving an extra shuffle to an already well-shuffled pack of cards. You know it will change your luck, but you don't know whether for better or worse. Had he stopped with the butterfly effect, an image of predictability giving way to pure randomness, then Lorenz would have produced no more than a piece of very bad news. But Lorenz saw more than randomness embedded in his weather model. He saw a fine geometrical structure, order masquerading as randomness. He turned his attention more and more to the mathematics of systems that never found a steady state, systems that almost repeated themselves but never quite succeeded. Everyone knew that the weather was such a system, aperiodic. Nature is full of others, animal populations that rise and fall almost regularly, epidemics that come and go on tantalizingly near regular schedules. To produce the rich repertoire of real earthly weather, the beautiful multiplicity of it, you could hardly wish for anything better than a butterfly effect. The butterfly effect acquired a technical name: sensitive dependence on initial conditions. And sensitive dependence on initial conditions was not an altogether new notion. It had a place in folklore. For want of a nail the shoe was lost. For want of a shoe the horse was lost. For want of a horse the rider was lost. For want of a rider the battle was lost. For want of a battle the kingdom was lost. Now, in science, as in life, it is well known that a chain of events can have a point of crisis that could magnify small changes. Lorenz put weather aside and looked for even simpler ways to produce this complex behavior. He found one in a system of just 3 equations. They were non-linear, meaning that they expressed relationships that were not strictly proportional, linear relationships that can be captured with a straight line on a graph. Linear equations are solvable, which makes them suitable for textbooks. Linear systems have an important modular virtue. You can take them apart and put them together again. The pieces add up. Non-linear systems generally cannot be solved and cannot be added together. In fluid systems and mechanical systems, the non-linear terms tend to be the features that people want to leave out when they try to get a good, simple understanding. Friction, for example. Without friction, a simple linear equation expresses the amount of energy you need to accelerate a hockey puck. With friction, the relationship gets complicated because the amount of energy changes depending on how fast the puck is already moving. Non-linearity means that the act of playing the game has a way of changing the rules. Lorenz's system traced a strange, distinctive shape, a kind of double spiral in 3 dimensions, like a butterfly with its 2 wings. The shape signaled pure disorder, since no point or pattern of points ever recurred. Yet it also signaled a new kind of order. Years later, Physicists would give wistful looks when they talked about Lorenz's paper on those equations, that beautiful marvel of a paper, but then it was talked about as if it were an ancient scroll preserving secrets of eternity. In the thousands of articles that made up the technical literature of chaos, few were cited more often than deterministic, non-periodic flow. For years, no single object would inspire more illustrations, even motion pictures, than the mysterious curve depicted at the end, the double spiral that became known as the Lorenz attractor. Revolution. The historian of science, Thomas Kuhn, describes a disturbing experiment conducted by a pair of psychologists in the 1940s. Subjects were given glimpses of playing cards, one at a time, and asked to name them. There was a trick, of course. A few of the cards were freakish. For example, a red six of spades or a black queen of diamonds. At high speed, the subjects sailed smoothly along. Nothing could have been simpler. They didn't see the anomalies at all. Shown a red six of spades, they would sing out either six of hearts or six of spades. But when the cards were displayed for longer intervals, the subjects started to hesitate. They became aware of a problem, but they were not sure what it was. A subject might say that he'd seen something odd, like a red border around a black heart. Eventually, as the pace was slowed even more, most subjects would catch on. They would see the wrong cards and make the mental shift necessary to play the game without error. Not everyone, though. A few suffered a sense of disorientation that brought real pain. "I can't make that suit out, whatever it is," said one. "It didn't even look like a card that time. I don't know what color it is now, or whether it's a spade or a heart. I'm not sure what a spade looks like. My God." Professional scientists, given brief, uncertain glimpses of nature's workings, are no less vulnerable to anguish and confusion when they come face to face with incongruity. And incongruity, when it changes the way a scientist sees, makes possible the most important advances, so Kuhn argues, and so the story of chaos suggests. Kuhn's notions of how scientists work and how revolutions occur drew as much hostility as admiration when he first published them in 1962, and the controversy has never ended. He pushed a sharp needle into the traditional view that science progresses by the accretion of knowledge, each discovery adding to the last, and that new theories emerge when new experimental facts require them. He deflated the view of science as an orderly process of asking questions and finding their answers. He emphasized a contrast between the bulk of what scientists do, working on legitimate, well-understood problems within their disciplines, and the exceptional, unorthodox work that create revolutions. Not by accident, he made scientists seem less than perfect rationalists. In Kuhn's scheme, normal science consists largely of mopping up operations. Experimentalists carry out modified versions of experiments that have been carried out many times before. Theorists add a brick here, reshape a cornice there, a wall of theory. It could hardly be otherwise. If all scientists had to begin from the beginning, questioning fundamental assumptions, they would be hard-pressed to reach the level of technical sophistication necessary to do useful work. Central to Kuhn's ideas is the vision of normal science as solving problems. Under normal conditions, the research scientist is not an innovator, but a solver of puzzles. And the puzzles upon which he concentrates are just those which he believes can be both stated and solved within the existing scientific tradition, Kuhn wrote. Then there are the revolutions. A new science arises out of one that has reached a dead end. Often a revolution has an interdisciplinary character. Its central discoveries often come from people straying outside the normal bounds of their specialties. The problems that obsess these theorists are not recognized as legitimate lines of inquiry. Thesis proposals are turned down or articles are refused publication. The theorists themselves are not sure whether they would recognize an answer if they saw one. They accept risk to their careers. A few free thinkers working alone, unable to explain where they're heading, afraid even to tell their colleagues what they are doing. That romantic image lies at the heart of Kuhn's scheme. And it has occurred in real life, time and time again, in the exploration of chaos. Every scientist who turned to chaos early had a story to tell of his discouragement or open hostility. Graduate students were warned that their careers could be jeopardized if they wrote theses in an untested discipline in which their advisors had no expertise. A particle physicist, hearing about this new mathematics, might begin playing with it on his own, thinking it was a beautiful thing, both beautiful and hard, but would feel that he could never tell his colleagues about it. Older professors felt they were suffering a kind of midlife crisis, gambling on a line of research that many colleagues were likely to misunderstand or resent. But they also felt an intellectual excitement that comes with the truly new. Even outsiders felt it, those who were attuned to it. To Freeman Dyson at the Institute for Advanced Study, the news of chaos came like an electric shock in the 1970s. Others felt that for the first time in their professional lives, they were witnessing a true paradigm shift, a transformation in a way of thinking. Those who recognized chaos in the early days agonized over how to shape their thoughts and findings into publishable form. Work fell between disciplines, for example, too abstract for physicists, yet too experimental for mathematicians. To some, the difficulty of communicating the new ideas and the ferocious resistance from traditional quarters showed how revolutionary the new science was. Shallow ideas can be assimilated. Ideas that require people to recognize or reorganize their picture of the world provoke hostility. A physicist at the Georgia Institute of Technology, Joseph Ford, started quoting Tolstoy. I know that most men, including those at ease with problems of the greatest complexity, can seldom accept even the simplest and most obvious truth, if it be such as would oblige them to admit the falsity of conclusions which they had delighted in explaining to colleagues, which they have proudly taught to others, and which they have woven thread by thread into the fabric of their lives. Many mainstream scientists remained only dimly aware of the emerging science. Some particularly traditional fluid dynamicists actively resented it. At first, the claims made on behalf of chaos sounded wild and unscientific, and chaos relied on mathematics that seemed unconventional and difficult. As the chaos specialists spread, some departments frowned on these somewhat deviant scholars. Others advertised for more. Some journals established unwritten rules against submissions on chaos. Other journals came forth to handle chaos exclusively. The chaoticists, or chaologists, such coinages could be heard, turned up with disproportionate frequency on the yearly lists of important fellowships and prizes. By the middle of the 80s, a process of academic diffusion had brought chaos specialists into influential positions with university bureaucracies. Centers and institutes were founded to specialize in nonlinear dynamics and complex systems. Chaos has become not just theory, but also method, not just a canon of beliefs, but also a way of doing science. Chaos has created its own technique of using computers, a technique that does not require the vast speed of Crays and Cybers, but instead favors modest terminals that allow flexible interaction. To chaos researchers, mathematics has become an experimental science, with the computer replacing laboratories full of test tubes and microscopes. Graphic images are the key. Stylistically, early chaos papers record the Benjamin Franklin era in the way they went back to first principles. As Kuhn notes, established sciences take for granted a body of knowledge that serves as a communal starting point for investigation. To avoid boring their colleagues, scientists routinely begin and end their papers with esoterica. By contrast, articles on chaos from the late 1970s onward sounded evangelical. From their preambles to their perorations, they declared new credos. They often ended with pleas for action. A modest cosmic mystery, the great red spot of Jupiter, a vast swirling oval like a giant storm that never moves and never runs down. Anyone who saw the pictures beamed across space from Voyager 2 in 1978 recognized the familiar look of turbulence on a hugely unfamiliar scale. It was one of the solar system's most venerable landmarks, the red spot roaring like an anguished eye amid a turbulence of boiling eyebrows, as John Updike described it. But what was it? 20 years after Lorenz, Smale and other scientists set in motion a new way of understanding nature's flows. The otherworldly weather of Jupiter proved to be one of the many problems awaiting the altered sense of nature's possibilities that came with the science of chaos. For 3 centuries, it had been a case of the more you know, the less you know. astronomers noticed a blemish on the great planet not long after Galileo first pointed his telescope at Jupiter. Robert Hooke saw it in the 1600s. Donati Creti painted it in the Vatican's picture gallery. As a piece of coloration, the spot called for little explaining, but telescopes got better, and knowledge bred ignorance. The last century produced a steady march of theories, one on the heels of another. For example, the lava flow theory. Scientists in the late 19th century imagined a huge oval lake of molten lava flowing out of a volcano. Or perhaps the lava had flowed out of a hole created by a planetoid striking a thin solid crust. The new moon theory. A German scientist suggested, by contrast, that the spot was a new moon on the point of emerging from the planet's surface. The egg theory. An awkward new fact. The spot was seen to be drifting slightly against the planet's background, so a notion put forward in 1939 viewed the spot as a more or less solid body floating in the atmosphere the way an egg floats in water. Variations of this theory, including the notion of a drifting bubble of hydrogen or helium, remained current for decades. The column of gas theory. Another new fact. Even though the spot drifted, somehow it never drifted far. So scientists proposed in the 60s that the spot was the top of a rising column of gas, possibly coming through a crater. Then came Voyager. Most astronomers thought the mystery would give way as soon as they could look closely enough, and indeed, the Voyager flyby provided a splendid album of new data. But the data in the end was not enough. The spacecraft pictures in 1978 revealed powerful winds and colorful eddies. In spectacular detail, astronomers saw the spot itself as a hurricane-like system of swirling flow, shoving aside the clouds embedded in zones of east-west wind that made horizontal stripes around the planet. Hurricane was the best description anyone could think of, but for several reasons it was inadequate. Earthly hurricanes are powered by the heat released when moisture condenses to rain. No moist processes derive the red spot. Hurricanes rotate in a cyclonic direction, counterclockwise above the equator and clockwise below. Like all earthly storms, the red spot's rotation is anticyclonic. And most important, hurricanes die out within days. Also, as astronomers studied the Voyager pictures, they realized that the planet was virtually all fluid in motion. They have been conditioned to look for a solid planet surrounded by a paper-thin atmosphere like Earth's. But if Jupiter had a solid core anywhere, it was far from the surface. The planet suddenly looked like one big fluid dynamics experiment. And there sat the red spot, turning steadily around and around, thoroughly unperturbed by the chaos around it. The spot became a Gestalt test. Scientists saw what their intuitions allowed them to see. A fluid dynamicist who thought of turbulence as random and noisy had no context for understanding an island of stability in its midst. Voyager had made the mystery doubly maddening by showing small-scale features of the flow, too small to be seen by the most powerful earthbound telescopes. The small scales displayed rapid disorganization, eddies appearing and disappearing within a day or less. Yet the spot was immune. What kept it going? What kept it in place? The National Aeronautics and Space Administration keeps its pictures in archives, a half dozen or so around the country. An archive is at Cornell University. Nearby, in the early 1980s, Philip Marcus, a young astronomer and applied mathematician, had an office. After Voyager, Marcus was one of a half dozen scientists in the United States and Britain who looked for ways to model the red spot. Freed from the ersatz hurricane theory, they found more appropriate analogues elsewhere. The Gulf Stream, for example, winding through the western Atlantic Ocean, twists and branches in subtly reminiscent ways. It develops little waves which turn into kinks, which turn into rings and spin off from the main current, forming slow, long-lasting anticyclonic vortices. Another parallel came from a peculiar phenomenon in meteorology known as blocking. Sometimes a system of high pressure sits offshore, slowly turning for weeks or months in defiance of the usual east-west flow. Blocking disrupted the global forecasting models, but it also gave the forecasters some hope, since it produced orderly features with unusual longevity. Marcus studied these NASA pictures for hours, the gorgeous Hasselblad pictures of men on the moon and the pictures of Jupiter's turbulence. Since Newton's laws apply everywhere, Marcus programmed a computer with a system of fluid equations. To capture Jovian weather meant writing rules for a mass of dense hydrogen and helium resembling an unlit star. The planet spins fast, each day flashing by in 10 Earth hours. The spin produces a strong Coriolis force, the sidelong force that shoves against a person walking across a merry-go-round, and the Coriolis force drives the spot. Where Lorenz used his tiny model of the Earth's weather to print crude lines on rolled paper, Marcus used far greater computer power to assemble striking color images. First he made contour plots. He could barely see what was going on. Then he made slides, and then he assembled the images into an animated movie. It was a revelation. In brilliant blues, reds, and yellows, a checkerboard pattern of rotating vortices coalesces into an oval with an uncanny resemblance to the great red spot in NASA's animated film of the real thing. You see, this large-scale spot, happy as a clam amid the small-scale chaotic flow, and the chaotic flow is soaking up energy like a sponge, he said. You see these little tiny filamentary structures in a background sea of chaos. The spot is a self-organizing system, created and regulated by the same non-linear twists that create the unpredictable turmoil around it. It is stable chaos. A geometry of nature. A picture of reality built up over the years in Benoit Mandelbrot's mind in 1960, it was a ghost of an idea, a faint, unfocused image. But Mandelbrot recognized it when he saw it, and there it was on the blackboard in Hendrik Hotaker's office. Mandelbrot was a mathematical jack-of-all-trades who'd been adopted and sheltered by the pure research wing of the International Business Machine Corporation. He'd been dabbling in economics, studying the distribution of large and small incomes in an economy. Hotaker, a Harvard economics professor, had invited Mandelbrot to give a talk, and when the young mathematician arrived at Litauer Center, the stately economics building just north of Harvard Yard, he was startled to see his finding already charted on the older man's blackboard. Mandelbrot made a querulous joke. How should my diagram have materialized ahead of my lecture? But Hotaker didn't know what Mandelbrot was talking about. The diagram had nothing to do with the income distribution. It represented 8 years of cotton prices. From Hotaker's point of view, too, there was something strange about this chart. Economists generally assumed that the price of a commodity like cotton danced to 2 different beats, one orderly and one random. Over the long term, prices will be driven steadily by real forces in the economy, the rise and fall of the New England textile industry, or the opening of international trade routes. Over the short term, prices would bounce around more or less randomly. Unfortunately, Hotaker's data failed to match his expectations. There were too many large jumps. Most price changes were small, of course, but the ratio of small changes to large was not as high as he had expected. The distribution did not fall off quickly enough. It had a long tail. The standard model for plotting variation was and is the bell-shaped curve. In the middle, where the hump of the bell rises, most data cluster around the average. On the sides, the low-high extremes fall off rapidly. A statistician uses a bell-shaped curve the way an internist uses a stethoscope as the instrument of first resort. It represents the normal distribution. The point is that when things vary, they try to stay near an average point, and they manage to scatter around the average in a reasonably smooth way. No matter how he plotted them, Hotaker could not make the changes in cotton prices fit the bell-shaped model. But they made a picture whose silhouette Mandelbrot was beginning to see in surprisingly disparate places. Unlike most mathematicians, he confronted problems by depending on his intuition about patterns and shapes. He mistrusted analysis, but he trusted his mental pictures. And he already had the idea that other laws with different behavior could govern random, stochastic phenomena. When he went back to the giant IBM research center in Yorktown Heights, New York, in the hills of northern Westchester County, he carried Hotaker's cotton data in a box of computer cards. Then he sent to the Department of Agriculture in Washington for more, dating back to 1900. Like scientists in other fields, economists were crossing the threshold into the computer era, slowly realizing that they would have the power to collect and organize and manipulate information on a scale that had been unimaginable before. Not all kinds of information were available, though, and information that could be rounded up still had to be turned into some usable form. The key-punch era was just beginning, too. In the hard sciences, investigators found it easier to amass their thousands or millions of data points. Economists, like biologists, dealt with a world of willful living beings. Economists studied the most elusive creatures of all. But at least the economist's environment produced a constant supply of numbers. From Mandelbrot's point of view, cotton prices made an ideal data source. The records were complete, and they were old, dating back continuously a century or more. Cotton was a piece of the buying and selling universe with a centralized market, and therefore centralized record-keeping, because at the turn of the century all the South's cotton flowed through the New York Exchange en route to New England, and Liverpool's prices were linked to New York's as well. Although economists had little to go on when it came to analyzing commodity prices or stock prices, that didn't mean they lacked a fundamental viewpoint about how price changes worked. On the contrary, they shared certain articles of faith. One was a conviction that small, transient changes had nothing in common with large, long-term changes. Fast fluctuations came randomly. The small-scale ups and downs during a day's transactions are just noise, unpredictable, uninteresting. Long-term changes, however, are a different species entirely. The broad swings of prices over months or years or decades are determined by deep macroeconomic forces. The trends of war or recession, forces that should, in theory, give way to understanding. On the one hand, the buzz of short-term fluctuation, on the other, the signal of long-term change. As it happened, that dichotomy had no place in the picture of reality that Mandelbrot was developing. Instead of separating tiny changes from grand ones, his picture bound them together. He was looking for patterns, not at one scale or another, but across every scale. It was far from obvious how to draw the picture he had in mind, but he knew there would have to be a kind of symmetry, not a symmetry of right and left or top and bottom, but rather a symmetry of large scales and small. Indeed, when Mandelbrot sifted the cotton price data through IBM's computers, he found the astonishing results he was seeking. The numbers that produced aberration from the point of view of normal distribution produced symmetry from the point of view of scaling. Each particular price change was random and unpredictable. But the sequence of changes was independent of scale. Curves for daily price changes and monthly price changes matched perfectly. Incredibly, analyzed Mandelbrot's way, the degree of variation had remained constant over a tumultuous 60-year period that saw 2 world wars and a depression. Within the most disorderly reams of data lived an unexpected kind of order. Given the arbitrariness of the numbers that he was examining, why, Mandelbrot asked himself, should any law hold at all? And why should it apply equally well to personal incomes and cotton prices? In truth, Mandelbrot's background in economics was as meager as his ability to communicate with economists. When he published an article on his findings, it was preceded by an explanatory article by one of his students who repeated Mandelbrot's material in economists' English. Mandelbrot moved on to other interests, but he took with him a growing determination to explore the phenomenon of scaling. It seemed to be a quality with a life of its own, a signature. In the history of chaos, Mandelbrot made his own way. Yet the picture of reality that was forming in his mind in 1960 evolved from an oddity into full-fledged geometry. To the physicists expanding on the work of people like Lorenz, Smale, York, and May, this prickly mathematician remained a sideshow, but his techniques and his language became an inseparable part of their new science. Benoit Mandelbrot was born in Warsaw in 1924 to a Lithuanian Jewish family. His father, a clothing wholesaler, his mother, a dentist. Alert to geopolitical reality, the family moved to Paris in 1936, drawn in part by the presence of Mandelbrot's uncle, Zolom Mandelbrot, a mathematician. When the war came, the family stayed just ahead of the Nazis once again, abandoning everything but a few suitcases and joining the stream of refugees who clogged the roads south from Paris. They finally reached the town of Toul. His schooling was irregular and discontinuous. He claimed never to have learned the alphabet or, more significantly, multiplication tables past the 5s. Still, he had a gift. When Paris was liberated, he took and passed the month-long oral and written admissions examination for École Normale and the École Polytechnique, despite his lack of preparation. Among other elements, the test had a vestigial examination in drawing, and Mandelbrot discovered a latent facility for copying the Venus de Milo. On the mathematical sections of the test, exercises in formal algebra and integrated analysis, he managed to hide his lack of training with the help of his geometrical intuition. He had realized that given an analytic problem, he could almost always think of it in terms of some shape in his mind. Given a shape, he could find ways of transforming it, altering its symmetries, making it more harmonious. Often his transformations led directly to a solution of the analogous problem. In physics and chemistry, where he could not apply geometry, he got poor grades. But in mathematics questions, he could never have answered using proper techniques, melted away in the face of his manipulations of shapes. In a 30-year journey from obscurity to eminence, he never saw his work embraced by the many disciplines toward which he directed it. Even mathematicians would say, without apparent malice, that whatever Mandelbrot was, he was not one of them. Early in his time at IBM, soon after his study of commodity prices, he came upon a practical problem of intense concern to his corporate patron. Engineers were perplexed by the problem of noise in telephone lines used to transmit information from computer to computer. Electric current carries the information in discrete packets, and engineers knew that the stronger they made the current, the better it would be at drowning out the noise. But they found that some spontaneous noise could never be eliminated. Once in a while it would wipe out a piece of signal, creating an error. Although by its nature the transmission noise was random, it was well known to come in clusters. Periods of errorless communication would be followed by periods of errors. By talking to the engineers, Mandelbrot soon learned that there was a piece of folklore about the errors that had never been written down, because it matched none of the standard ways of thinking. The more closely they looked at the clusters, the more complicated the patterns of errors seemed. Mandelbrot provided a way of describing the distribution of errors that predicted exactly the observed patterns. Yet it was exceedingly peculiar. For one thing, it made it impossible to calculate an average rate of errors. On average, in Mandelbrot's schemes, errors approached infinite sparseness. His description worked by making deeper and deeper separations between periods of clean transmission and periods of errors. Suppose you divided a day into hours. An hour might pass with no errors at all. Then an hour might contain errors. Then an hour might pass with no errors. But suppose you then divided the hour with errors into smaller periods of 20 minutes. You would find that here, too, some periods would be completely clean, while some would contain a burst of errors. In fact, Mandelbrot argued, contrary to intuition, that you could never find a time during which errors were scattered continuously. Within any burst of errors, no matter how short, there would always be periods of completely error-free transmission. Furthermore, he discovered a consistent geometric relationship between the bursts of errors and the spaces of clean transmission. On scales of an hour or a second, the proportion of error-free periods remained constant. Once, to Mandelbrot's horror, a batch of data seemed to contradict his scheme, but it turned out that the engineers had failed to record the most extreme cases, on the assumption that they were irrelevant. Engineers had no framework for understanding Mandelbrot's description, but mathematicians did. In effect, Mandelbrot was duplicating an abstract construction known as the Cantor set, after the 19th century mathematician George Cantor. To make a Cantor set, you start with the interval of numbers from 0 to 1, represented by a line segment. Then you remove the middle third. That leaves 2 segments, and you remove the middle third of each, from 1/9 to 2/9, and from 7/9 to 8/9. That leaves 4 segments, and you remove the middle third of each, and so on to infinity. What remains? A strange dust of points, arranged in clusters, infinitely many yet infinitely sparse. Mandelbrot was thinking of transmission errors as a Cantor set arranged in time. This highly abstract description had practical weight for scientists trying to decide between different strategies of controlling error. In particular, it meant that instead of trying to increase signal strength to drown out more and more noise, engineers should settle for a modest signal, accept the inevitability of errors, and use a strategy of redundancy to catch and correct them. Mandelbrot also changed the way IBM's engineers thought about the cause of noise. Bursts of errors had always sent the engineers looking for a man sticking a screwdriver somewhere, but Mandelbrot's scaling patterns suggested that the noise would never be explained on the basis of specific local events. Mandelbrot turned to other data, drawn from the world's rivers. Egyptians have kept records of the height of the Nile for millennia. It is a matter of more than passing concern. The Nile suffers unusually great variation, flooding heavily in some years and subsiding in others. Mandelbrot classified the variation in terms of two kinds of effects, common in economics as well, which he called the Noah and Joseph effects. The Noah effect means discontinuity. When a quantity changes, it can change almost arbitrarily fast. Economists traditionally imagined that prices change smoothly, rapidly or slowly, as the case may be, but smoothly in the sense that they pass through all the intervening levels on their way from one point to another. That image of motion was borrowed from physics, like much of the mathematics applied to economics, but it was wrong. Prices can change in instantaneous jumps, as swiftly as a piece of news can flash across a teletype wire, and 1,000 brokers can change their minds. The stock market strategy was doomed to fail, Mandelbrot argued, if it assumed that a stock would have to sell for $50 at some point on its way down from $60 to $10. The Joseph effect means persistence. There came 7 years of great plenty throughout the land of Egypt, and there shall arise after them 7 years of famine. If the biblical legend meant to imply periodicity, it was oversimplified, of course, but floods and droughts do persist. Despite an underlying randomness, the longer a place has suffered drought, the likelier it is to suffer more. Furthermore, mathematical analysis of the Nile's height showed that persistence applied over centuries as well as over decades. The Noah and Joseph effects push in different directions, but they add up to this. Trends in nature are real, but they can vanish as quickly as they come. Discontinuity, bursts of noise, Cantor dusts, phenomena like these had no place in the geometrics of the past 2,000 years. The shapes of classical geometry are lines and planes, circles and spheres, triangles and cones. They represent a powerful abstraction of reality, and they inspired a powerful philosophy of Platonic harmony. Euclid made of them a geometry that lasted 2 millennia, the only geometry still that most people ever learn. Artists found an ideal beauty in them. Ptolemaic astronomers built a theory of the universe out of them, but for understanding complexity, they turn out to be the wrong kind of abstraction. Clouds are not spheres, Mandelbrot is fond of saying. Mountains are not cones. Lightning does not travel in a straight line. The new geometry mirrors a universe that is rough, not rounded, scabrous, not smooth. It is a geometry of the pitted, pocked, and broken up, the twisted, tangled, and intertwined. The understanding of nature's complexity awaited a suspicion that the complexity was not just random, not just accident. It required a faith that the interesting feature of a lightning bolt's path, for example, was not its direction, but rather the distribution of zigs and zags. Mandelbrot's work made a claim about the world. The claim was that such odd shapes carry meaning. The pits and tangles are more than blemishes distorting the classic shapes of Euclidean geometry. They are often the keys to the essence of a thing. What is the essence of a coastline, for example? Mandelbrot asked this question in a paper that became a turning point for his thinking. How long is the coast of Britain? Mandelbrot had come across the coastline question in an obscure posthumous article by an English scientist, Louis F. Richardson, who groped with a surprising number of the issues that later became part of chaos. He wrote about numerical weather prediction in the 1920s, studied fluid turbulence by throwing a sack of white parsnips into the Cape Cod Canal, and asked in a 1926 paper, does the wind possess a velocity? The question, at first sight foolish, improves on acquaintance, he wrote. Wondering about coastlines and wiggly national borders, Richardson checked encyclopedias in Spain and Portugal, Belgium and the Netherlands, and discovered discrepancies of 20% in the estimated lengths of their common frontiers. Mandelbrot's analysis of this question struck listeners as either painfully obvious or absurdly false. He found that most people answered the question in one of two ways. I don't know, it's not my field, or I don't know, but I'll look it up in the encyclopedia. In fact, he argued, any coastline is, in a sense, infinitely long. In another sense, the answer depends on the length of your ruler. Consider one plausible method of measuring. A surveyor takes a set of dividers, opens them to a length of 1 yard, and walks them along the coastline. Now, the resulting number of yards is just an approximation of the true length, because the dividers skip over twists and turns smaller than 1 yard, but the surveyor writes the number down anyway. Then he sets the dividers to a smaller length, say 1 foot, and repeats the process. He arrives at a somewhat greater length because the dividers will capture more of the detail, and it will take more than 3 one-foot steps to cover the distance previously covered by a 1 yard step. He writes this new number down, sets the dividers at 4 inches, and starts again. This mental experiment using imaginary dividers is a way of quantifying the effect of observing an object from different distances at different scales. An observer trying to estimate the length of England's coastline from a satellite will make a smaller guess than an observer trying to walk its coves and beaches, who will make a smaller guess in turn than a snail negotiating every pebble. Since Euclidean measurements, length, depth, thickness, failed to capture the essence of irregular shapes, Mandelbrot turned to a different idea, the idea of dimension. Dimension is a quality with a much richer life for scientists than for non-scientists. We live in a three-dimensional world, meaning that we need 3 numbers to specify a point. For example, longitude, latitude, and altitude. The 3 dimensions are imagined as directions at right angles to one another. This is still the legacy of Euclidean geometry, where space has 3 dimensions. A plane has 2, a line has 1, and a point has 0. The process of abstraction that allowed Euclid to conceive of 1 or 2-dimensional objects spills over easily into our use of everyday objects. A road map, for all practical purposes, is quintessential 2-dimensional thing, a piece of a plane. It uses its 2 dimensions to carry information of a precisely 2-dimensional kind. In reality, of course, road maps are as 3-dimensional as everything else, but their thickness is so slight and so irrelevant to their purpose that it can be forgotten. Effectively, a road map remains 2-dimensional even when it's folded up. In the same way, a thread is effectively 1-dimensional, and a particle has effectively no dimension at all. Then, what is the dimension of a ball of twine? Mandelbrot answered, it depends on your point of view. From a great distance, the ball is no more than a point, with 0 dimensions. From closer, the ball is seen to fill spherical space, taking up 3 dimensions. From closer still, the twine comes into view, and the object becomes effectively 1-dimensional, though the 1 dimension is certainly tangled up around itself in a way that makes use of 3-dimensional space. And on toward microscopic perspectives. Twine turns to 3-dimensional columns. The columns resolve themselves into 1-dimensional fibers. The solid material dissolves into 0-dimensional points. What about in between? Well, surely there was no clear boundary at which a ball of twine changes from a 3-dimensional to a 1-dimensional object. Yet, far from being a weakness, the ill-defined nature of these transitions led to a new idea about the problem of dimensions. Mandelbrot moved beyond dimensions, 0, 1, 2, 3, to a seeming impossibility, fractional dimensions. The notion is a conceptual high-wire act. For non-mathematicians, it requires a willing suspension of disbelief. Yet it proves extraordinarily powerful. Fractional dimension becomes a way of measuring qualities that otherwise have no clear definition. The degree of roughness or brokenness or irregularity in an object. A twisting coastline, for example, despite its immeasurability in terms of length, nevertheless has a certain characteristic degree of roughness. Mandelbrot specified ways of calculating the fraction and dimension of real objects, given some technique of constructing a shape or given some data, and he allowed his geometry to make a claim about the irregular patterns that he had studied in nature. The claim was that the degree of irregularity remains constant over different scales. Surprisingly often, the claim turns out to be true. Over and over again, the world displays a regular irregularity. One wintry afternoon in 1975, aware of the parallel currents emerging in physics, preparing his first major work for publication in book form, Mandelbrot decided he needed a name for his shapes, his dimensions, and his geometry. His son was home from school, and Mandelbrot found himself thumbing through the boy's Latin dictionary. He came across the adjective fractus, from the verb frangere, to break. The resonance of the main English cognates, fracture and fraction, seemed appropriate. Mandelbrot created the word, noun and adjective, English and French, fractal. In pursuing this path, Mandelbrot had two great advantages over the few other mathematicians who have thought about such shapes. One was his access to the computing resources that go with the name of IBM. Here was another task ideally suited to the computer's particular form of high-speed idiocy. Just as meteorologists needed to perform the same few calculations of millions of neighboring points in the atmosphere, Mandelbrot needed to perform an easy program transformation again and again and again. Ingenuity could conceive of transformations. Computers could draw them, sometimes with unexpected results. The early 20th century mathematicians quickly reached a barrier of hard calculation, like the barrier faced by early photobiologists without microscopes. In looking into a universe of finer and finer detail, the imagination can carry one only so far. Mandelbrot's picture of reality was beginning to come into focus now. His studies of irregular patterns in natural processes and his exploration of infinitely complex shapes had an intellectual intersection, a quality of self-simplicity. Above all, fractal meant self-similar. Self-similarity is symmetry across scale. It implies recursion, pattern inside of a pattern. Mandelbrot's price charts and river charts displayed self-similarity because not only did they produce detail at finer and finer scales, they also produced detail with certain constant measurements. Self-similarity is an easily recognizable quality. Its images are everywhere in the culture, in mirrors, or in the cartoon notion of a fish eating a smaller fish, eating a smaller fish, eating a smaller fish. How big is it? How long does it last? These are the most basic questions a scientist can ask about a thing. They are so basic to the way people conceptualize the world that it is not easy to see that they imply a certain bias. They suggest that size and duration, qualities that depend on scale, are qualities with meaning, qualities that can help describe an object or classify it. When a biologist describes a human being or a physicist describes a quark, how big and how long are indeed appropriate questions. In their gross physical structure, animals are very much tied to a particular scale. Imagine a human being scaled up to twice its size, keeping all proportions the same, and you imagine a structure whose bones will collapse under its weight. Scale is important. The physics of earthquake behavior is mostly independent of scale. A large earthquake is just a scaled-up version of a small earthquake. That distinguishes earthquakes from animals. For example, a 10-inch animal must be structured quite differently from a 1-inch animal. A 100-inch animal needs a different architecture still, if its bones are not to snap under the increased mass. Clouds, on the other hand, are scaling phenomena like earthquakes. Their characteristic irregularity, describable in terms of fractal dimension, changes not at all as they are observed on different scales. That is why air travelers lose all perspective on how far away a cloud is. Without help from cues such as haziness, a cloud 20 feet away can be indistinguishable from 2,000 feet away. Indeed, analysis of satellite pictures has shown an invariant fractal dimension in clouds observed from hundreds of miles away. It's hard to break the habit of thinking of things in terms of how big they are and how long they last. But the claim of fractal geometry is that for some elements of nature, looking for a characteristic scale becomes a distraction. Hurricane. By definition, it is a storm of a certain size, but the definition is imposed by people on nature. In reality, atmospheric scientists are realizing that tumult in the air forms a continuum from the gusty swirling of litter on a city street corner to the vast cyclonic systems visible from space. Categories mislead. The ends of the continuum are of a piece with the middle. It happens that the equations of fluid flow are in many contexts dimensionless, meaning that they apply without regard to scale. Scaled-down airplane wings and ship propellers can be tested in wind tunnels and laboratory basins, and with some limitations, small storms act like large storms. Blood vessels, from aorta to capillaries, form another kind of continuum. They branch and divide and branch again until they become so narrow that blood cells are forced to slide through single file. The nature of their branching is fractal. Their structure resembles one of the monstrous imaginary objects conceived by Mandelbrot's turn-of-the-century mathematicians. As a matter of physiological necessity, blood vessels must perform a bit of dimensional magic. The circulatory system must squeeze a huge surface area into a limited volume. In terms of the body's resources, blood is expensive and space is at a premium. The fractal structure nature has devised works so efficiently that in most tissue no cell is ever more than 3 or 4 cells away from a blood vessel. Yet the vessels and blood take up little space, no more than about 5% of the body. It is, as Mandelbrot put it, the Merchant of Venice syndrome. Not only can't you take a pound of flesh without spilling blood, you can't take a milligram. This exquisite structure, actually 2 intertwining trees of veins and arteries, is far from exceptional. The body is filled with such complexity. In the digestive tract, tissue reveals undulations within undulations. The lungs, too, need to pack the greatest possible surface into the smallest space. An animal's ability to absorb oxygen is roughly proportional to the surface area of its lungs. Typical human lungs pack in a surface bigger than a tennis court. As an added complication, the labyrinth of windpipes must merge efficiently with the arteries and veins. Not immediately, but a decade after Mandelbrot published his physiological speculations, some theoretical biologists began to find fractal organization controlling structures all through the body. The standard exponential description of bronchial branching proved to be quite wrong. A fractal description turned out to fit the data. The urinary collecting system proved fractal. The biliary duct in the liver, the network of special fibers in the heart that carry pulses of electric current to the contracting muscles. Mandelbrot glided matter-of-factly from pulmonary and vascular trees to real botanical trees, trees that need to capture sun and resist wind, with fractal branches and fractal leaves. The theoretical biologists began to speculate that fractal scaling was not just common, but universal in morphogenesis. They argued that understanding how such patterns were encoded and processed had become a major challenge to biology. If one scientist announces that a thing is probably true and another demonstrates it with vigor, which one has done more to advance science? Is the making of a conjecture an act of discovery, or is it just a cold-blooded staking out of a claim? Mathematicians have always faced such issues, but the debate became more intense as computers began to play their new role. Those who used computers to conduct experiments became more like laboratory scientists, playing by rules that allowed discovery without the usual theorem proof of the standard mathematics paper. Mandelbrot's book was wide-ranging and stuffed with the minutiae of mathematical history. Wherever chaos led, Mandelbrot had some basis to claim that he'd been there first. Little did it matter that most readers found his references obscure or even useless. They had to acknowledge his extraordinary intuition for the direction of advances in fields that he had never actually studied, from seismology to physiology. It was something uncanny and sometimes irritating. Even an admirer would cry with exasperation, Mandelbrot didn't have everybody's thoughts before they did. It hardly matters. The face of genius need not always wear an Einstein saint-like mien. In the end, the word fractal came to stand for a way of describing, calculating, and thinking about shapes that are irregular and fragmented, jagged and broken up. Shapes from the crystalline curves of snowflakes to the discontinuous dusts of galaxies. A fractal curve implies an organizing structure that lies hidden among the hideous complication of such shapes. High school students could understand fractals and play with them. Simple computer programs to draw fractal pictures made the rounds of personal computer hobbyists. Mandelbrot found his most enthusiastic acceptance among applied scientists working with oil or rock or metals, particularly in corporate research centers. By the middle of the 1980s, vast numbers of scientists at Exxon's huge research facility, for example, worked on fractal problems. At General Electric, fractals became an organizing principle in the study of polymers and also, though his work was conducted secretly, in problems of nuclear reactor safety. In Hollywood, fractals found their most whimsical application in the creation of phenomenally realistic landscapes, earthly and extraterrestrial, in special effects for movies. Patterns discovered in the early 1970s, with complex boundaries between orderly and chaotic behavior, had unsuspected regularities that could only be described in terms of the relation of large scales to small. The structures that provided the key to nonlinear dynamics proved to be fractal. And on the most immediate, practical level, fractal geometry also provided a set of tools that were taken up by physicists, chemists, seismologists, metallurgists, probability theorists, and physiologists. These researchers were convinced, and they tried to convince others, that Mandelbrot's new geometry was nature's own. They made an irrefutable impact on orthodox mathematics and physics as well, but Mandelbrot himself never gained the full respect of those communities. Even so, they had to acknowledge him. One mathematician told friends that he had awakened one night still shaking from a nightmare. In this dream, the mathematician was dead and suddenly heard the unmistakable voice of God. "You know," he remarked, "there really was something to that Mandelbrot." The notion of self-similarity strikes ancient chords in our culture. An old strain in Western thought honors the idea. Leibniz imagined that a drop of water contained a whole teeming universe, containing in turn water drops and new universes within. When sperm were first discovered, each was thought to be a homonucleus, a human, tiny but fully formed. But self-similarity withered as a scientific principle for a good reason. It didn't fit the facts. The early sense of self-similarity as an organizing principle came from the limitations on the human experience of scale. How else to imagine the very great and the very small, the very fast and the very slow, but extensions of the known? The myth died hard as the human vision was extended by telescopes and microscopes. The first discoveries were realizations that each change of scale brought new phenomena and new kinds of behavior. For modern particle physicists, the process has never ended. Every new accelerator, with its increase in energy and speed, extends science's field of view to tinier particles and briefer timescales, and every extension seems to bring new information. At first blush, the idea of consistency on new scales seems to provide less information. In part, that is because a parallel trend in science has been toward reductionism. Scientists break things apart and look at them one at a time. If they want to examine the interaction of subatomic particles, they put two or three together. There is complication enough. The power of self-similarity, though, begins at much greater levels of complexity. It is a matter of looking at the whole. Self-similarity was implicit in Edward Lorenz's work. It was part of his intuitive understanding of the fine structure of the maps made by his system of equations, a structure he could sense but not see on the computers available in 1963. Scaling also became part of a movement in physics that led more directly than Mandelbrot's own work to the discipline known as chaos. Even in distant fields, scientists were beginning to think in terms of theories that used hierarchies of scales, as in evolutionary biology, where it became clear that a full theory would have to recognize patterns of development in genes, in individual organisms, in species, and in families of species all at once. Paradoxically, perhaps the appreciation of scaling phenomena must have come from the same kind of expansion of human vision that had killed the earlier naive ideas of self-similarity. By the late 20th century, in ways never before conceivable, images of the incomprehensibly small and the unimaginably large became part of everyone's experience. The culture saw photographs of galaxies and of atoms. No one had to imagine what the universe might be like on microscopic or telescopic scales. Microscopes and telescopes made those images part of everyday experience. Given the eagerness of the mind to find analogies in experience, new kinds of comparison between large and small were inevitable, and some of them were productive. It was to be the physicists, after all, who made a new science of chaos. Mandelbrot provided an indispensable language and a catalogue of surprising pictures of nature. As Mandelbrot himself acknowledged, his program described better than it explained. He could list elements of nature along with their fractal dimensions, seacoasts, river networks, tree bark galaxies, and scientists could use those numbers to make predictions. But physicists wanted to know more. They wanted to know why. There were forms in nature, not visible forms, but shapes embedded in the fabric of motion, waiting to be revealed. Universality. A few dozen yards upstream from a waterfall, a smooth flowing stream seems to intuit the coming drop. The water begins to speed and shudder. Individual rivulets stand out like coarse throbbing veins. Mitchell Feigenbaum stands at streamside. He's sweating slightly in sports coat and corduroys and puffing on a cigarette. He's been walking with friends, but they had gone on ahead to the quieter pools upstream. Suddenly, in what might be a demented high-speed parody of a tennis spectator, he starts turning his head from side to side. You can focus on something, a bit of foam or something. If you move your head fast enough, you can all of a sudden discern the whole structure of the surface, and you can feel it in your stomach. He draws in more smoke from his cigarette. But for anyone with a mathematical background, if you look at this stuff, or you see clouds with all their puffs on top of puffs, or stand at a seawall in a storm, you know that you really don't know anything. Order in chaos. It was science's oldest cliché. The idea of hidden unity and common underlying form in nature had an intrinsic appeal, and it had an unfortunate history of inspiring pseudo-scientists and cranks. When Feigenbaum came to Los Alamos National Laboratory in 1974, a year shy of his 30th birthday, he knew that if physicists were to make something of the idea now, they would need a practical framework, a way to turn ideas into calculations. It was far from obvious how to make a first approach to the problem. Feigenbaum was hired by Peter Carruthers, a calm, deceptively genial physicist who came from Cornell in '73 to take over the theoretical division. His first act was to dismiss a half-dozen senior scientists. Los Alamos provides its staff with no equivalent of university tenure, and to replace them with some bright young researchers of his own choosing. As a scientific manager, he had strong ambition, but he knew from experience that good science cannot always be planned. Feigenbaum brought to Los Alamos a conviction that his science had failed to understand hard problems, non-linear problems. Although he had produced almost nothing as a physicist, he had accumulated an unusual intellectual background. He had a sharp working knowledge of the most challenging mathematical analysis, new kinds of computational technique that pushed most scientists to their limits. He had managed not to purge himself of some seemingly unscientific ideas from 18th century romanticism. He wanted to do science that would be new. He began by putting aside any thought of understanding real complexity and instead turned to the simplest non-linear equations that he could find. The mystery of the universe first announced itself to the 4-year-old Mitchell Feigenbaum through a Silvertone radio sitting in his parents' living room in the Flatbush section of Brooklyn soon after the war. He was dizzy with the thought of music arriving from no tangible cause. Now, the phonograph, on the other hand, he thought he understood. His grandmother had given him a special dispensation to put on the 78s. His father was a chemist who worked for the Port of New York Authority and later for Clairol. His mother taught in the city's public schools. Mitchell first decided to become an electrical engineer, a sort of professional known in Brooklyn to make a good living. Later, he realized that what he wanted to know about a radio was more likely to be found in physics. He was one of a generation of scientists raised in the outer boroughs of New York who made their way to brilliant careers via the great public high schools, in his case Samuel J. Tilden, and then City College. Growing up smart in Brooklyn was in some measure a matter of steering an uneven course between the world of mind and the world of other people. He was immensely gregarious when very young, which he regarded as a key to not being beaten up, but something clicked when he realized he could learn things. He became more and more detached from his friends. Ordinary conversation couldn't hold his interest. Sometime in his last year of college, it struck him that he had missed his adolescence, and he made a deliberate project out of regaining touch with humanity. He would sit silently in the cafeteria, listening to students chatting about shaving or food, and gradually he relearned much of the science of talking to people. He graduated in 1964, went on to MIT, where he got his doctorate in elementary particle physics in 1970. Then he spent a fruitless 4 years at Cornell and at the Virginia Polytechnic Institute. Fruitless, that is, in terms of the steady publication of work on manageable problems that is essential for a young university scientist. Postdocs were supposed to produce papers. Occasionally, an advisor would ask Feigenbaum what had happened to some problem, and he'd say, "Oh, I understood it." Newly installed at Los Alamos, Carruthers, formidable scientist in his own right, prided himself on his ability to spot talent. He looked not for intelligence, but for a sort of creativity that seemed to flow from some magic gland. He always remembered the case of Kenneth Wilson, another soft-spoken Cornell physicist, who seemed to be producing absolutely nothing. Anyone who talked to Wilson for long realized that he had a deep capacity for seeing into physics. So the question of Wilson's tenure became a subject of serious debate. The physicists willing to gamble on his unproven potential prevailed, and it was as if a dam burst. Not one, but a flood of papers came forth from Wilson's desk drawers, including work that won him the Nobel Prize in 1982. Wilson's great contribution to physics, along with work by two other physicists, Leo Kadanoff and Michael Fisher, was an important ancestor of chaos theory. These men, working independently, were all thinking in different ways about what happened in phase transitions. They were studying the behavior of matter near the point where it changes from one state to another, from liquid to gas, or from unmagnetized to magnetized. As singular boundaries between two realms of existence, phase transitions tend to be highly non-linear in their mathematics. The smooth and predictable behavior of matter in any one phase tends to be little help in understanding the transitions. A pot of water on the stove heats up in regular way until it reaches the boiling point. But then the change in temperature pauses while something quite interesting happens at the molecular interface between liquid and gas. As Kadanoff viewed the problem in the 1960s, phase transitions pose an intellectual puzzle. Think of a block of metal being magnetized. As it goes into an ordered state, it must make a decision. The magnet can be oriented one way or the other. It is free to choose, but each tiny piece of the metal must make the same choice. How? Somehow, in the process of choosing, the atoms of the metal must communicate information to one another. Kadanoff's insight was that the communication can be most simply described in terms of scaling. In effect, he imagined dividing the metal into boxes. Each box communicates with its immediate neighbors. The way to describe that communication is the same as the way to describe the communication of any atom with its neighbors. Hence, the usefulness of scaling. The best way to think of the metal is in terms of a fractal-like model with boxes of all different sizes. Much mathematical analysis and much experience with real systems was needed to establish the power of the scaling idea. Kadanoff felt that he had taken an unwieldy business and created a world of extreme beauty and self-containedness. Part of the beauty lay in its universality. Kadanoff's idea gave a backbone to the most striking fact about critical phenomena, namely that these seemingly unrelated transitions, the boiling of liquids, the magnetizing of metals, all follow the same rules. As a graduate student at MIT, Feigenbaum had an experience that stayed with him for many years. He was walking with friends around the Lincoln Reservoir in Boston. He was developing a habit of taking 4- and 5-hour walks, attuning himself to the panoply of impressions and ideas that would flow through his mind. On this day, he became detached from the group and walked alone. He passed some picnickers, and as he moved away, he glanced back every so often, hearing the sounds of their voices, watching the motions of hands gesticulating or reaching for food. Suddenly, he felt that the tableau had crossed some threshold into incomprehensibility. The figures were too small to be made out. The action seemed disconnected, arbitrary, random. What faint sounds reached him had lost meaning. The ceaseless motion and incomprehensible bustle of life. Feigenbaum recalled the words of Gustav Mahler describing a sensation that he tried to capture in the third movement of his Second Symphony, like the motions of dancing figures in a brilliantly lit ballroom into which you look from the dark night outside, and from such a distance that the music is inaudible. Life may appear senseless to you. Feigenbaum was listening to Mahler, reading Goethe, immersing himself in their high romantic attitudes. Inevitably, it was Goethe's Faust he most reveled in, soaking up its combination of the most passionate ideas about the world with the most intellectual. Without some romantic inclinations, he surely would have dismissed a sensation like his confusion at the reservoir. After all, why shouldn't phenomena lose meaning as they are seen from greater distances? Physical laws provide a trivial explanation for their shrinking. On second thought, the connection between shrinking and loss of meaning was not so obvious. Why should it be that as things become small, they also become incomprehensible? He tried, quite seriously, to analyze this experience in terms of the tools of theoretical physics, wondering what he could say about the brain's machinery of perception. You see some human transactions and you make deductions about them. Given the vast amount of information available to your senses, how does your decoding apparatus sort it out? Clearly, or almost clearly, the brain does not own any direct copies of stuff in the world. There is no library of forms and ideas against which to compare the images of perception. Information is stored in a plastic way, allowing fantastic juxtapositions and leaps of imagination. Some chaos exists out there, and the brain seems to have more flexibility than classical physics in finding the order of it. When Feigenbaum began to think about nonlinearity at Los Alamos, he realized that his education had taught him nothing useful. To solve a system of nonlinear differential equations was impossible, notwithstanding the special examples constructed in textbooks. He read through texts of nonlinear flows and oscillations and decided that little existed to help a reasonable physicist. His computational equipment consisting solely of pencil and paper, Feigenbaum decided to start with a simple equation from population biology. It happened to be the equation high school students use in geometry to graph a parabola. It can be written as y equals r, x minus x. Every value of x produces a value of y, and the resulting curve expresses the relation of the two numbers for the range of values. If x, this year's population, is small, then y, next year's, is small but larger than x. The curve is rising steeply. If x is in the middle of the range, then y is large, but the parabola levels off and falls, so that if x is large, then y will be small again. That is what produces the equivalent of population crashes in ecological modeling, preventing unrealistic, unrestrained growth. The point was to use this simple calculation not once, but repeated endlessly as a feedback loop. The output of one calculation was fed back as input for the next. To see what happened graphically, the parabola helped enormously. In spirit, nothing could have been further removed from the complex calculations of standard physics. Instead of a labyrinth scheme to be solved one time, this was a simple calculation performed over and over again. The numerical experimenter would watch, like a chemist peering at a reaction bubbling away inside a beaker. Here, the output was just a string of numbers, and it did not always converge to a steady final state. It could end up oscillating back and forth between two values, or it could keep on changing chaotically as long as anyone cared to watch. The choice among these different possible behaviors depended on the value of the tuning parameter. Feigenbaum carried out numerical work of this faintly experimental sort and at the same time tried more traditional theoretical ways of analyzing nonlinear functions. Even so, he couldn't see the whole picture of what this equation could do, but he could see that the possibilities were already so complicated that they would be viciously hard to analyze. He also knew that three Los Alamos mathematicians, Nicholas Metropolis, Paul Stein, and Myron Stein, had studied such maps in 1971, and now Paul Stein warned him that the complexity was frightening indeed. If this simplest of equations already proved intractable, what about the far more complicated equations that a scientist would write down for real systems? Feigenbaum put the whole problem on the shelf. In the brief history of chaos, this one innocent-looking equation provides the most succinct example of how different sorts of scientists looked at one problem in many different ways. To the biologists, it was an equation with a message. Simple systems can do complicated things. To Metropolis, Stein, and Stein, the problem was to catalog a collection of topological patterns without reference to any numerical values. They would begin the feedback process at a particular point and watch the succeeding values bounce from place to place on the parabola. As the values moved to the right or the left, They wrote down sequences of R's and L's. These sequences had some interesting features to a mathematician. They always seemed to repeat in the same special order. But to a physicist, they looked obscure and tedious. No one realized it then, but Lorenz had looked at the same equation in 1964 as a metaphor for a deep question about climate. The question was so deep that almost no one thought to ask it before. Does a climate exist? That is, does the Earth's weather have a long-term average? Most meteorologists, then as now, took the answer for granted. Surely any measurable behavior, no matter how it fluctuates, must have an average. Yet, on reflection, it's far from obvious. As Lorenz pointed out, the average weather for the past 12,000 years has been notably different than the average for the previous 12,000, when most of North America was covered by ice. Was there one climate that changed to another for some physical reason? Or is there an even longer-term climate within which those periods were just fluctuations? Or is it possible that a system like the weather may never converge to an average? Lorenz asked a second question. Suppose you could actually write down the complete set of equations that govern the weather. In other words, suppose you had God's own code. Could you then use the equations to calculate average statistics for temperature or rainfall? If the equations were linear, the answer would be an easy yes. But they're nonlinear. Since God has not made the actual equations available, Lorenz instead examined the quadratic difference equation. Lorenz first examined what happened as the equation was iterated, given some parameter. With low parameters, he saw the equation reaching a stable fixed point. There, certainly, the system produced a climate in the most trivial sense possible. The weather never changed. With higher parameters, he saw the possibility of oscillation between 2 points. And there, too, the system converged to a simple average. But, beyond a certain point, Lorenz saw that chaos ensues. Since he was thinking about climate, he asked not only whether continual feedback would produce periodic behavior, but also what the average output would be, and recognized that the answer was that the average, too, fluctuated unstably. When the parameter value was changed ever so slightly, the average might change dramatically. By analogy, the Earth's climate might never settle reliably into an equilibrium with average long-term behavior. As he continued to explore the changing masks of dynamical systems, Lorenz realized that systems slightly more complicated could produce other kinds of unexpected patterns. Hiding within a particular system could be more than one stable solution. An observer might see one kind of behavior over a very long time, yet a completely different kind of behavior could be just as natural for the system. Such a system is called intransitive. It can stay in one equilibrium or the other, but not both. Only a kick from outside can force it to change states. In a trivial way, a standard pendulum clock is an intransitive system. A steady flow of energy comes in from a wind-up spring or a battery through an escapement mechanism. A steady flow of energy is drained out by friction. The obvious equilibrium state is a regular swinging motion. If a passerby bumps the clock, the pendulum might speed up or slow down from the momentary jolt, but it will quickly return to its equilibrium as well, a second valid solution to its equations of motion, and that is the state in which the pendulum is hanging straight down and not moving. A less trivial intransitive system, perhaps with several distinct regions of utterly different behavior, could be climate itself. Climatologists who use global computer models to simulate the long-term behavior of the Earth's atmosphere and oceans have known for several years that their models allow at least one dramatically different equilibrium. During the entire geological past, this alternative climate has never existed. But it could be an equally valid solution to the system of equations governing the Earth. It is what some climatologists call the white Earth climate, an Earth whose continents are covered by snow and whose oceans are covered by ice. A glaciated Earth would reflect 70% of the incoming solar radiation and so would stay extremely cold. The lowest layer of the atmosphere, the troposphere, would be much thinner. The storms that would blow across the frozen surface would be much smaller than the storms we know. In general, the climate would be less hospitable to life as we know it. Computer models have such a strong tendency to fall into the white Earth equilibrium that climatologists find themselves wondering why it has never come about. it may simply be a matter of chance. To push the Earth's climate into the glaciated state would require a huge kick from some external source. But Lorenz described yet another plausible kind of behavior called almost intransitivity. An almost intransitive system displays one sort of average behavior, still fluctuating within certain bounds. Then, for no reason whatsoever, it shifts into a different sort of behavior, still fluctuating, but producing a different average. The people who design computer models are aware of Lorenz's discovery, but they try at all costs to avoid almost intransitivity. It's too unpredictable. Their natural bias is to make models with a strong tendency to return to the equilibrium we measure every day on the real planet. Then, to explain large changes in climate, they look for external causes, changes in the Earth's orbit around the Sun, for example. Yet it takes no great imagination for a climatologist to see that almost intransitivity might well explain why the Earth's climate has drifted in and out of long ice ages at mysterious, irregular intervals. If so, no physical cause need be found for the timing. The ice ages may simply be a byproduct of chaos. The modern scientist nurses a certain nostalgia for the HP 65 handheld calculator. In the few years of its supremacy, this machine changed many scientists' working habits forever. For Feigenbaum, it was the bridge between pencil and paper and a style of working with computers that had not yet been conceived. He knew nothing of Lorenz, but in the summer of 1975, at a gathering in Aspen, Colorado, he heard Steve Smale talk about some of the mathematical qualities of the same quadratic difference equation. Smale seemed to think that there was some interesting open question about the exact point at which the mapping changes from periodic to chaotic. As always, Smale had a sharp instinct for questions worth exploring. Feigenbaum decided to look into it once more. With his calculator, he began to use a combination of analytic algebra and numerical exploration to piece together an understanding of the quadratic map, concentrating on the boundary region between order and chaos. Metaphorically, but only metaphorically, he knew that his region was like the mysterious boundary between smooth flow and turbulence in a fluid. En route to chaos in this region was a cascade of period doublings, the splitting of 2 cycles into 4 cycles, 4 cycles into 8 cycles, and so on. These splittings made a fascinating pattern. They were the points at which a slight change in fecundity, for example, might lead a population of gypsy moths to change from a 4-year cycle to an 8-year cycle. Feigenbaum decided to begin by calculating the exact parameter values that produced the splittings. In the end, it was the slowness of the calculator that led him to a discovery that August. It took ages, minutes in fact, to calculate the exact parameter value of each period doubling. The higher up the chain he went, the longer it took. With a fast computer and with a printout, Feigenbaum might have observed no pattern. But he had to write the number down by hand, and then he had to think about them while he was waiting, and then, to save time, he had to guess where the next answer would be. Yet, all in an instant, he saw that he did not have to guess. There was an unexpected regularity hidden in the system. The numbers were converging toward the horizon in a perspective drawing. If you know how big to make any 2 telephone poles, you know all the rest. The ratio of the second to the first will also be the ratio of the third to the second, and so on. The period doublings were not just coming faster and faster, but they were coming faster and faster at a constant rate. Why should this be so? Ordinarily, the presence of geometric convergence suggests that something somewhere is repeating itself on different scales. But if there was a scaling pattern inside this equation, no one had ever seen it. Feigenbaum calculated the ratio of convergence to the finest precision possible on his machine, 3 decimal places, and came up with a number, 4.669. Did this particular ratio mean anything? Feigenbaum did what anyone would do who cared about numbers. He spent the rest of the day trying to fit the number to all the standard constants, pi and so forth. It was a variant of none. Feigenbaum knew what he had, because geometric convergence meant that something in this equation was scaling, and he knew that scaling was important. All of renormalization theory depended on it. In an apparently unruly system, scaling meant that some quality was being preserved while everything else changed. Some regularity lay beneath the turbulent surface of the equation, but where? It was hard to see what to do next. Summer turns rapidly to autumn in the rarefied Los Alamos air, and October had nearly ended when Feigenbaum was struck by an odd thought. He knew that Metropolis, Stein and Stein had looked at other equations as well, and had found that certain patterns carried over from one sort of function to another. The same combinations of R's and L's appeared, and they appeared in the same order. One function had involved the sign of a number, a twist that made Feigenbaum's carefully worked-out approach to the parabola equation irrelevant. He would have to start over. Calculating a trigonometry function made the process that much slower, and Feigenbaum wondered whether, as with the simpler version of the equation, he would be able to use a shortcut. Sure enough, scanning the numbers, he realized that they were again converging geometrically. It was simply a matter of calculating the convergence rate of this new equation. Again, his precision was limited, but he got a result to 3 decimal places, 4.669. It was the same number. Incredibly, this trigonometric function was not just displaying a consistent geometric regularity, it was displaying a regularity that was numerically identical to that of a much simpler function. No mathematical or physical theory existed to explain why two equations, so different in form and meaning, should lead to the same result. Feigenbaum called for Stein. Stein was not prepared to believe the coincidence on such scanty evidence. The precision was low after all. Nevertheless, Feigenbaum also called his parents in New Jersey to tell them that he'd stumbled across something profound. He told his mother it was going to make him famous. Then he started trying other functions, anything he could think of that went through a sequence of bifurcations on the way to disorder. Every one produced the same number. Feigenbaum had played with numbers all his life. When he was a teenager, he knew how to calculate logarithms and sines that most people would look up in tables. But he had never learned to use any computer bigger than his hand calculator, and in this he was typical of physicists and mathematicians who tended to disdain the mechanistic thinking that computer work implied. Now, though, it was time. He asked a colleague to teach him Fortran, and by the end of the day, for a variety of functions, he'd calculated his constant to 5 decimal places, 4.66920. That night, he read about double precision in the manual, and the next day he got as far as 4.669201690, enough precision to convince Stein. Feigenbaum wasn't quite sure that he convinced himself, though. He'd set out to look for regularity. That was what understanding mathematics meant. But he had also set out knowing that particular kinds of equations, just like particular physical systems, behave in special characteristic ways. These equations were simple after all. Feigenbaum understood the quadratic equation, he understood the sine equation, the mathematics was trivial. Yet something in the heart of these very different equations, repeating over and over again, created a single number. He'd stumbled upon something, perhaps just a curiosity, perhaps a new law of nature. Imagine that a prehistoric zoologist decides that some things are heavier than other things. They have some abstract quality he calls weight. And he wants to investigate this idea scientifically. He's never actually measured weight, but he thinks he has some understanding of the idea. He looks at big snakes and little snakes, big bears and little bears, and he guesses that the weight of these animals might have some relationship to their size. He builds a scale and starts weighing snakes. To his astonishment, every snake weighs the same. To his consternation, every bear weighs the same too. And to his further amazement, bears weigh the same as snakes. They all weigh 4.669201690. Clearly, weight is not what he supposed. The whole concept requires rethinking. Rolling streams, swinging pendulums, electronic oscillators, many physical systems went through a transition on the way to chaos, and those transitions had remained too complicated for analysis. These were all systems whose mechanics seemed perfectly well understood. Physicists knew all the right equations, yet moving from the equations to an understanding of global long-term behavior seemed impossible. Unfortunately, equations for fluids, even pendulums, were far more challenging than the simple one-dimensional logistic map. But Feigenbaum's discovery implied that those equations were beside the point. They were irrelevant. When order emerged, it suddenly seemed to have forgotten what the original equation was. Quadratic or trigonometric, the result was the same. The whole tradition of physics is that you isolate the mechanisms and all the rest flows, he said. That's completely falling apart. Here you know the right equations, but they're just not helpful. You add up all the microscopic pieces, and you find that you cannot extend them to the long term. They're not what's important in the problem. It completely changes what it means to know something. Although the connection between numerics and physics was faint, Feigenbaum had found evidence that he needed to work out a new way of calculating complex nonlinear problems. So far, all available techniques had depended on the details of the functions. If the function was a sine function, Feigenbaum's carefully worked out calculations were sine calculations. His discovery of universality meant that all those techniques would have to be thrown out. The regularity had nothing to do with sines. It had nothing to do with parabolas. It had nothing to do with particular function. But why? It was frustrating. Nature had pulled back a curtain for an instant and offered a glimpse of unexpected order. What else was behind the curtain? When inspiration came, it was in the form of a picture, a mental image of two small wavy forms and one big one. That was all, a bright, sharp image, etched in his mind, no more perhaps than the visible top of a vast iceberg of mental processing that had taken place below the waterline of consciousness. It had to do with scaling, and it gave Feigenbaum the path he needed. Feigenbaum was carrying out a program in physics, and strange as it seemed, it was almost a kind of experimental physics. Numbers and functions were his object of study, instead of mesons and quarks. They had trajectories and orbits. He needed to inquire into their behavior. He needed, in a phrase that later became a cliché of the new science, to create intuition. His accelerator and his cloud chamber were the computer. Along with his theory, he was building a methodology. Ordinarily, a computer user would construct a problem, feed it in, and wait for the machine to calculate its solution. One problem, one solution. Feigenbaum and the chaos researchers who followed needed more. They needed to do what Lorenz had done, to create miniature universes and observe their evolution. Feigenbaum quickly discovered how ill-suited the computer facilities of Los Alamos were for the style of computing he wanted to develop. Despite enormous resources far greater than at most universities, Los Alamos had few terminals capable of displaying graphs and pictures, and those few were in the weapons division. Feigenbaum wanted to take numbers and plot them as points on a map. He had to resort to the most primitive method conceivable. Long rolls of printout paper with lines made by printing rows of spaces followed by an asterisk or a plus sign. The official policy at Los Alamos held that one big computer was worth far more than many little computers, a policy that went with the one problem, one solution tradition. Little computers were discouraged. Furthermore, any division's purchase of a computer would have to meet stringent government guidelines and a formal review. Only later, with the budgetary complicity of the theoretical division, did Feigenbaum become the recipient of a $20,000 desktop calculator. Then he could change his equations and pictures on the run, tweaking them and tuning them, playing the computer like a musical instrument. For now, the only terminals capable of serious graphics were in high-security areas behind the fence in local parlance. Feigenbaum had to use a terminal hooked up by telephone lines to a central computer. The reality of working in such an arrangement made it hard to appreciate the raw power of the computer at the other end of the line. Even the simplest tasks took minutes. To edit a line of program meant pressing return and waiting while the terminal hummed incessantly, and the central computer played its electronic round-robin with other users across the laboratory. While he was computing, he was thinking. What new mathematics could produce the multiple scaling patterns that he was observing? Something about these functions must be recursive, he realized, self-referential, the behavior of one guided by the behavior of another hidden inside it. The wavy image that had come to him in a moment of inspiration expressed something about the way one function could be scaled to match another. He applied the mathematics of renormalization group theory, with its use of scaling to collapse infinities into manageable quantities. In the spring of 1976, he entered a mode of existence more intense than any he had lived through. He would concentrate, as if in a trance, programming furiously, scribbling with his pencil, programming again. He could not call C Division for help, because that would mean signing off the computer to use the telephone, and reconnection was chancy. He couldn't stop for more than 5 minutes, thought, because the computer would automatically disconnect his line. Every so often the computer would go down anyway, leaving him shaking with adrenaline. He worked for 2 months without pause. His functional day was 22 hours. He would try to go to sleep in a kind of buzz and awaken 2 hours later with his thoughts exactly where he'd left them. His diet was strictly coffee. Even when healthy and a peace Feigenbaum subsisted exclusively on the reddest possible meat, coffee, and red wine, his friends speculated that he must be getting his vitamins from cigarettes. In the end, a doctor called it off. He prescribed a modest regimen of Valium and an enforced vacation. But by then, Feigenbaum had created a universal theory. Universality made the difference between beautiful and useful. Mathematicians, beyond a certain point, care little whether they are providing a technique for calculation. Physicists, beyond a certain point, need numbers. Universality offered the hope that by solving an easy problem, physicists could solve much harder problems. The answers will be the same. Further, by placing his theory in the framework of the renormalization group, Feigenbaum gave it a clothing that physicists would recognize as a tool for calculating, almost something standard. But what made universality useful also made it hard for physicists to believe. Universality meant that different systems would behave identically. Of course, Feigenbaum was only studying simple numerical functions, but he believed that his theory expressed a natural law about systems at the point of transition between orderly and turbulent. The physical implication was that real-world systems would behave in the same recognizable way, and that, furthermore, it would be measurably the same. Feigenbaum's universality was not just qualitative, it was quantitative, not just structural, but metrical. It extended not just to patterns, but to precise numbers. To a physicist, that strained credulity. Years later, Feigenbaum still kept in a desk drawer, where he could get at them quickly, his rejection letters. By then, he had all the recognition he needed. His Alamos work had won him prizes and awards that brought prestige and money, but it still rankled that editors at the top academic journals had deemed his work unfit for publication for 2 years after he began submitting it. The notion of a scientific breakthrough so original and unexpected that it cannot be published seems a slightly tarnished myth. Modern science, with its vast flow of information and its impartial system of peer review, is not supposed to be a matter of taste. One editor who sent back a Feigenbaum manuscript recognized years later that he'd rejected a paper that was a turning point for the field. Yet he still argued that the paper had been unsuited to his journal's audience of applied mathematicians. In the meantime, even without publication, Feigenbaum's breakthrough became a superheated piece of news in certain circles of mathematics and physics. The kernel of theory was disseminated the way most science is not disseminated, through lectures and preprints. Feigenbaum described his work at conferences, and requests for photocopies of his papers came in by the score, and then by the hundreds. A movement had begun, and the discovery of universality spurred it forward. In the summer of 1977, 2 physicists, Joseph Ford and Giulio Casati, organized the first conference on a science called chaos. It was held in a gracious villa in Como, Italy, a tiny city at the southern foot of the lake of the same name, a stunningly deep blue catch basin for the melting snow from the Italian Alps. 100 people came, mostly physicists, but also curious scientists from other fields. Mitch had seen universality and found out how it scaled and worked out a way of getting to chaos that was intuitively appealing, Ford said. It was the first time we had a clear model that everybody could understand. And it was one of those things whose time had come. In disciplines from astronomy to zoology, people were doing the same things, publishing in their narrow disciplinary journals, just totally unaware that the other people were around. They thought they were by themselves, and they were regarded as a bit eccentric in their own areas. They had exhausted the simple questions you could ask and begun to worry about phenomena that were a bit more complicated. And these people were just weepingly grateful to find out that everybody else was there too. Later, Feigenbaum lived in a bare space, a bed in one room, a computer in another, and in the third, 3 black electronic towers for playing his solidly Germanic record collection. His one experiment in home furnishing, the purchase of an expensive marble coffee table while he was in Italy, had ended in failure. He received a parcel of marble chips. Piles of papers and books lined the walls. He talked rapidly, his long hair, graying now, mixed with brown, sweeping back from his forehead. Something dramatic happened in the 20s. For no good reason, physicists stumbled upon an essentially correct description of the world around them, because the theory of quantum mechanics is in some sense essentially correct. It tells you how you can take dirt and make computers from it. It's the way we've learned to manipulate our universe. It's the way chemicals are made and plastics and whatnot. One knows how to compute with it. It's an extravagantly good theory, except at some level it doesn't make good sense. Some part of the imagery is missing. If you ask what the equations really mean and what is the description of the world according to this theory, it's not a description that entails your intuition of the world. You can't think of a particle moving as though it has a trajectory. You're not allowed to visualize it that way. If you start asking more and more subtle questions, what does this theory tell you the world looks like? In the end, it's so far out of normal, a normal way of picturing things, that you run into all sorts of conflicts. Now, maybe that's the way the world really is. But you don't really know that there isn't another way of assembling all this information that doesn't demand so radical a departure from the way in which you intuit things. There's a fundamental presumption in physics that the way you understand the world is that you keep isolating its ingredients until you understand the stuff that you think is truly fundamental. Then you presume that the other things you don't understand are details. The assumption is that there are a small number of principles that you can discern by looking at things in their pure state. This is the true analytic notion. And then somehow you put these together in more complicated ways when you want to solve more dirty problems if you can. As the collective knew well, most traditional instruction in physics glossed over nonlinearity. A few thought of nonlinearity as a creative force. Yet it was nonlinearity that created the mysteriously beautiful patterns of strange attractors. Nonlinear was a word that you only encountered in the back of the book, Farmer says. A physics student would take a math course, and the last chapter will be on nonlinear equations. You would usually skip that. Shaw and his colleagues had to turn their raw enthusiasm into a scientific program. They had to ask questions that could be answered and that would be worth answering. They sought ways of connecting theory and experiment. There, they felt, was a gap that needed to be closed. Before they could even begin, they had to learn what was known and what was not. And this itself was a formidable challenge. They did not know it, but their problems were emblematic of the hurdles faced by pioneers in chaos of many widely separated institutions. A handful of researchers, often working alone, afraid to discuss their unorthodox ideas with their colleagues. The Santa Cruz students were hindered by the tendency of communication to travel piecemeal in science, particularly when a new subject jumps across the established subdisciplines. Often they had no idea whether they were on new or old territory, and indeed some of their work paralleled discoveries by Soviet mathematicians. They quickly realized that many sorts of questions could be asked about the possible behaviors of simple physical systems and the strange attractors that they produced. What are their characteristic shapes? What does the geometry reveal about the physics of the related physical systems? A physicist wants to make measurements. What was there in these elusive, moving images to measure? Shaw and the others tried to isolate the special qualities that made strange attractors so enchanting. Unpredictability was one. But where were the calipers to gauge such a quality? By now, the collective was meeting regularly in an outsized old Santa Cruz house not far from the beach. The house accumulated flea market furniture and computer equipment, much of which was devoted to the roulette problem. In their meetings, the physicists developed a working style, a routine of throwing out ideas and filtering them through some sieve of practicality, reading the literature, and conceiving papers of their own. Making a bridge from the strange attractors they knew so well to the experiments of classical physics, the young physicists had grown more comfortable with such ideas than had any of their older colleagues. By living with strange attractors day and night, they convinced themselves that they recognized them in the flapping, shaking, beating, swaying phenomena of everyday lives. They had a game they would play. They would ask, how far away is the nearest strange attractor? Was it that rattling automobile fender? That flag snapping erratically in a steady breeze? A fluttering leaf? You don't see something until you have the right metaphor to let you perceive it, Shaw said. Before long, his astrophysicist friend Burke was quite convinced that the speedometer in his car was rattling in the non-linear fashion of a strange attractor. And Shaw, settling on an experimental project that would occupy him for years to come, adopted as homely a dynamical system as any physicist could imagine, a dripping faucet. As a generator of organization, the dripping faucet offers little to work with. But for a beginning investigator of chaos, the dripping faucet proved to have certain advantages. Everyone already has a mental picture of it. The data stream is as one-dimensional as could be, a rhythmic drumbeat of single points measured in time. None of these qualities could be found in systems that the Santa Cruz group explored later, the human immune system, for example, or the troublesome beam effect that was inexplicably degrading the performance of colliding particle beams at the Stanford Linear Accelerator Center to the north. In the dripping faucet, the single line of data is all there is. And it isn't even a continuously varying velocity or temperature, just a list of drip times. The drips can be regular, or, as anyone can discover by adjusting a kitchen faucet, they can turn irregular and seemingly unpredictable. Asked to organize an attack on such a system, a traditional physicist might begin by making as complete a physical model as possible. The processes governing the creation and breaking off of drips are understandable, if not quite so simple as they might seem. One important variable is the rate of flow. Now, this had to be slow compared to most hydrodynamic systems. Shaw usually looked at drop rates of 1 to 10 per second, which meant a flow rate of 30 to 300 gallons per fortnight. Other variables include the viscosity of the fluid and the surface tension. A drop of water hanging off a faucet, waiting to break off, assumes a complicated three-dimensional shape, and the calculation of the shape alone was, as Shaw said, a state-of-the-art computer calculation. A drop filling with water is like a little elastic bag of surface tension, oscillating this way and that, gaining mass and stretching its walls until it snaps off. A physicist, trying to model the drip problem completely by writing down sets of equations and trying to solve them, would find himself lost in a deep, deep thicket. An alternative approach would be to forget about the physics and look only at the data, as though it were coming out of a black box. Given a list of numbers representing intervals between drips, could an expert in chaotic dynamics find something useful to say? Indeed, as it turned out, methods could be devised for organizing such data and working backwards into the physics, and these methods became critical to the applicability of chaos to real-world problems. Shaw began halfway between these extremes by making a sort of caricature of a complete physical model. He roughly summarized drip physics by imagining a weight hanging from a spring. The weight steadily grows. The spring stretches, and the weight hangs lower and lower. At a certain point, a portion of the weight would break off. The amount that would detach, Shaw supposed arbitrarily, would depend strictly on the speed of the descending weight when it reached the cutoff point. Then, of course, the remaining weight would bounce back up, as springs do, with oscillations that graduate students learn to model using standard equations. The interesting feature of the model, the only interesting feature, was a non-linear twist that made chaotic behavior possible. The precise timing of drip depended on the flow rate, but it also depended on how the springiness of this bag of surface tension interacted with the steadily increasing weight. If a drop started off its life already moving downward, then it would break off sooner. If it happened to be on the rebound, it would be able to fill with a bit more water before it snaps. Would Shaw's model generate as much complexity as a real faucet? And would the complexity be of the same kind? Shaw found himself sitting in the laboratory in the physics building, a big plastic tub of water over his head, a tube running down to a premium quality hardware store brass nozzle. As each drop fell, it interrupted a light beam, and a microcomputer in the next room recorded the time. At the same time, Shaw had his equations up and running on the analog computer, producing a stream of imaginary data. One day, he performed some show and tell for the faculty, a pseudo-colloquium, as Crutchfield said, because graduate students were not permitted to give formal colloquiums. Shaw played a tape of a faucet making its drumbeat on a piece of tin, and he had his computer going click, click, click in a crisp syncopation, revealing patterns to the ear. His listeners could hear the deep structure in this seemingly disorderly system, but to go further, the group needed a way of taking raw data from any experiment and working backward to equations and strange attractors that characterized chaos. With a more complicated system, one variable could be plotted against another, relating changes in temperature or velocity to the passage of time. But the dripping faucet provided only a series of times, so Shaw tried a technique that may have been the Santa Cruz group's cleverest and most enduring practical contribution to the progress of chaos. It was a method of reconstructing an unseen strange attractor, and it could be applied to any series of data at all. For the dripping faucet data, Shaw made a graph in which the horizontal axis represented a time interval between a pair of drops, and the vertical axis represented the time interval between the next pair. If 150 milliseconds passed between drop 1 and drop 2, and then 150 milliseconds passed between drop 2 and drop 3, he'd plot a point at the position of 150, 150. That was all there was to it. If the dripping was regular, the graph would be suitably dull. Every point would land at the same place. The graph would be a single dot, or almost. Actually, the first difference between the computer dripping faucet and the real dripping faucet was that the real version was subject to noise and exceedingly sensitive. Shaw ended up doing most of his work at night, when foot traffic in the physics corridors was lightest. Noise meant that instead of the single dot predicted by theory, he would see a slightly fuzzy blob. Each member of the collective was taken aside from time to time for heart-to-heart talks. They were warned that even if somehow a way could be found to justify doctorates, no one will be able to help the students find jobs in a non-existent field. This may be a fad, the faculty would say, and then where would you be? Yet outside of the redwood shelter of the Santa Cruz Hills, chaos was creating its own scientific establishment, and the Dynamical Systems Collective had to join it. The turning point was the surprise appearance at a midwinter meeting in condensed matter physics in Laguna Beach in 1978. The collective was not invited, but it went nonetheless, bundling itself into Shaw's 1959 Ford ranch-style station wagon, an automobile known as the Cream Dream. Just in case, the group brought some equipment, including a huge television monitor and a videotape. When an invited speaker cancelled at the last minute, Shaw took his place. The timing was perfect. Chaos had attained the status of buzzword, but few of the physicists attending the conference knew what it meant. So Shaw began by explaining the different kinds of attractors, from ordinary to strange. First, steady states, where everything stops, then periodic cycles, where everything oscillates, then chaotic strange attractors, everything else. He demonstrated with his computer graphics on videotape. Audio-visual aids gave us an edge, he said. We could hypnotize them with flashing lights. He illuminated the Lorenz attractor and the dripping faucet. As the flow rate was increased, the system would go through a sudden change in character, a bifurcation. Now, drops would fall in pairs. One interval might be 150 milliseconds, and the next might be 80, so the graph would show two fuzzy blobs, one centered at 150 to 180, and the other at 80 to 150. The real test came when the pattern became chaotic. If it were truly random, points would be scattered all over the graph. But if strange attractors were hidden in the data, it might reveal itself as a coalescence of fuzziness into distinguishable structures. Often, 3 dimensions were necessary to see the structure, but that was no problem. The technique could easily be generalized to higher dimensional graph making. Instead of plotting each interval against the next, the scientist would plot each interval against the next but one. It was a trick, a gimmick. Ordinarily, a 3-dimensional graph required knowledge of 3 independent variables in a system. The trick gave 3 variables for the price of 1. It reflected the faith of these scientists that order was so deeply ingrained in apparent disorder that it would find a way of expressing itself even to experimenters who do not know which physical variables to measure. As Farmer says, when you think about a variable, the evolution of it must be influenced by whatever other variables it's interacting with. Their values must somehow be contained in the history of that thing. Somehow their mark must be there. In the case of Shaw's dripping faucet, the pictures illustrated the point. In 3 dimensions especially, the patterns emerged, resembling loopy trails of smoke left by an out-of-control skywriting plane. Shaw was able to match plots of the experimental data with data produced by his analog computer model, the main difference being that the real data was always fuzzier, smeared out by noise. Even so, the structure was unmistakable. As the months went on, the transition from rebel to physicist was slow. Every so often, sitting in a coffee house or working in their lab, one or another of the students would have to fight back amazement that their scientific fantasy had not ended. God, we're still doing this, and it still makes sense, as Jim Crutchfield would say. We're still here. How far is it going to go? Most of the physics faculty found itself in a difficult position. We had no advisor, nobody telling us what to do, said Shaw. We were in an adversary role for years, and it continues to this day. We were never funded at Santa Cruz. Every one of us worked for considerable periods of time without pay. And it was a shoestring operation the entire way with no intellectual or other guidance. The talk was a popular triumph, and in the audience were several members of the Santa Cruz faculty, seeing chaos for the first time through the eyes of their colleagues. The collective couldn't go on forever. The closer it came to the real world of science, the closer it came to unraveling. Its members began thinking about their individual futures, and they began collaborating with established physicists and mathematicians elsewhere. Having learned to look for strange attractors in flapping flags and rattling speedometers, the scientists made a point of finding the symptoms of chaos all through the current literature of physics. Peculiarities that had been dismissed as noise, surprising fluctuations, regularity mixing with irregularity, now began to be explained in the terms of the new science. By the time the collective departed, some in the Santa Cruz faculty had turned to chaos too. They were joining a movement. Chemists, ecologists, economists, climatologists all now find themselves trying to reconstruct strange attractors from crude data, just as Shaw had in his dripping faucet studies. Experts on finance use the techniques developed by the Santa Cruz group to sift through decades of daily stock market data, for example, seeking patterns they believe must be there. Many physiologists now believe that chaos provides a way of predicting and perhaps treating erratic rhythms in the processes that govern life, from breathing to heartbeats to brain function. It was in 1980 when Shaw finished his dissertation, 1981 for Farmer, 1982 for Packard. Crutchfield's appeared in 1983, typographical hodgepodge, interweaving typed pages with no less than 11 papers already published in the journals of physics and mathematics. Now he was studying video feedback loops. Farmer worked on fat fractals and modeled the dynamics of the human immune system. Packard explored spatial chaos and the formation of snowflakes. Only Shaw seemed reluctant to join the mainstream. Several times he came close to quitting science altogether. As his friend said, he was oscillating. 2 decades ago, Edward Lorenz was thinking about the atmosphere. Benoit Mandelbrot was an unknown IBM mathematician. Mitchell Feigenbaum, an undergraduate at the City College of New York. Doyne Farmer, a boy growing up in New Mexico. Most practicing scientists shared a set of beliefs about complexity. They held these beliefs so closely that they didn't need to put them into words. Only later did it become possible to say what these beliefs were and to bring them out for examination. Simple systems behave in simple ways. A mechanical contraption like a pendulum, a small electrical circuit, an idealized population of fish in a pond, as long as these systems could be reduced to a few perfectly understood, perfectly deterministic laws, their long-term behavior would be stable and predictable. Complex behavior implies complex cause. A mechanical device, an electrical circuit, a wildlife population, a fluid flow, a biological organ, a particle beam, an atmospheric storm, a national economy, a system that was visibly unstable, unpredictable, or out of control must either be governed by a multitude of independent components or subject to random external influences. Different systems behave differently. A neurobiologist who spent a career studying the chemistry of the human neuron without learning anything about memory or perception, an aircraft designer who used wind tunnels to solve aerodynamic problems without understanding the mathematics of turbulence, an economist who analyzed the psychology of purchasing decisions without gaining an ability to forecast large-scale trends, scientists like these, knowing that the components of their disciplines were different, took it for granted that the complex systems made up of billions of these components must also be different. Now, all that has changed. In the intervening 20 years, physicists, mathematicians, biologists, and astronomers have created an alternative set of ideas. Simple systems give rise to complex behavior. Complex systems give rise to simple behavior. And most important, the laws of complexity hold universally, caring not at all for the details of a system's constituent atoms. For the mass of practicing scientists, particle physicists or neurologists or even mathematicians, the change did not matter immediately. They continued to work on research problems within their disciplines. But they were aware of something called chaos. They knew that some complex phenomena had been explained, and they knew that other phenomena suddenly seemed to need new explanations. A scientist studying chemical reactions in a laboratory or tracking insect populations in a 3-year field experiment or modeling ocean temperature variations couldn't respond in the traditional way to the presence of unexpected fluctuations or oscillations. That is, by ignoring them. For some, that meant trouble. On the other hand, pragmatically, they knew that money was available from the federal government and from corporate research facilities for this faintly mathematical kind of science. More and more of them realized that chaos offered a fresh way to proceed with old data, forgotten in desk drawers because they had proved too erratic. More and more felt the compartmentalization of science as an impediment to their work. More and more felt the futility of studying parts in isolation from the whole. For them, chaos was the end of the reductionist program in science. Uncomprehension, resistance, anger, acceptance. Those who had promoted chaos longest saw all of these. Joseph Ford of the Georgia Institute of Technology remembered lecturing to a thermodynamics group in the 1970s and mentioning that there was a chaotic behavior in the Duffing equation, a well-known textbook model for a simple oscillator subject to friction. To Ford, the presence of chaos in the Duffing equation was a curious fact, just one of those things he knew to be true, although several years passed before it was published in Physical Review letters. But he might as well have told a gathering of paleontologists that dinosaurs had feathers. They knew better. When I said that, Jesus Christ, the audience began to bounce up and down. It was, my daddy played with the Duffing equation, or my granddaddy played with the Duffing equation, and nobody's seen anything like what you're talking about. You would really run across resistance to the notion that nature is complicated. What I didn't understand was the hostility. Comfortable in his Atlanta office, the winter sun setting outside, Ford sipped soda from oversized mugs with the word chaos painted in bright colors. His younger colleague, Ronald Fox, talked about his own conversion, soon after buying an Apple II computer for his son, at a time when no self-respecting physicist would buy such a thing for his work. Fox heard that Mitchell Feigenbaum had discovered universal laws guiding the behavior of feedback function, and he decided to write a short program that would let him see the behavior of the Apple display. He saw it all painted across the screen, pitchfork bifurcations, stable lines breaking in 2, then 4, then 8, the appearance of chaos itself, and within the chaos, the astonishing geometric regularity. In a couple of days you could redo all of Feigenbaum, Fox said. Self-teaching by computing persuaded him and others who might have doubted a written argument. Some scientists played with such programs for a while and then stopped. Others could not help but be changed. Fox was one of those who'd remained conscious of the limits of standard linear science. He knew he had habitually set the hard, non-linear programs and problems aside. In practice, a physicist would always end up saying, "This is a problem that's going to take me to the handbook of special functions, which is the last place I want to go, and I'm sure as hell not going to get on a machine and do it. I'm too sophisticated for that." The general picture of non-linearity got a lot of people's attention, slowly at first, but increasingly, Fox said, everybody everybody that looked at it, it bore fruit for. You now look at any problem you looked at before, no matter what science you're in. There was a place where you could quit looking at it because it became non-linear. Now you know how to look at it, and you go back. Ford said, if an area begins to grow, it has to be because some clump of people feel that there's something it offers them. That if they modify their research, the rewards could be very big. To me, chaos is like a dream. It offers the possibility that if you come over and play the game, you can strike the mother lode. The journal Nature carried a running debate about whether the Earth's climate followed a strange attractor. Economists looked for recognizable strange attractors in stock market trends, but so far had not found them. Dynamicists hoped to use the tools of chaos to explain fully developed turbulence. Albert Liebschaber of the University of Chicago was turning his elegant experimental style to the service of turbulence, creating a liquid helium box thousands of times larger than his tiny cell of 1977. Whether such experiments, liberating fluid disorder in both space and time, would find simple attractors, no one knew. As the physicist Bernardo Huberman said, if you had a turbulent river and you put a probe in it and said, look, here's a low-dimensional strange attractor, we would all take off our hats and look. Chaos was the set of ideas persuading all these scientists that they were members of a shared enterprise. Physicist or biologist or mathematician, they believed that simple, deterministic systems could breed complexity, that systems too complex for traditional mathematics could yet obey simple laws, and that whatever their particular field, their task was to understand complexity itself. Let us look again at the laws of thermodynamics, wrote James Lovelock, author of the Gaia hypothesis. It is true that at first sight they read like the notice at the gate of Dante's hell, but the second law is one piece of technical bad news from science that has established itself firmly in the non-scientific culture. Everything tends toward disorder. Any process that converts energy from one form to another must lose some as heat. Perfect efficiency is impossible. The universe is a one-way street. Entropy must always increase in the universe and in any hypothetical isolated system within it. However expressed, the second law is a rule from which there seems no appeal. In thermodynamics, that is true, but the second law has had a life of its own in intellectual realms far removed from science, taking the blame for disintegration of societies, economic decay, the breakdown of manners, and many other variations on the decadent theme. These secondary metaphorical incarnations of the second law now seem especially misguided. In our world, complexity flourishes, and those looking to science for a general understanding of nature's habits will be better served by the laws of chaos. Somehow, after all, as the universe ebbs towards its final equilibrium in the featureless heat bath of maximum entropy, it manages to create interesting structures. Thoughtful physicists concerned with the workings of thermodynamics realize how disturbing is the question of, as one put it, how a purposeless flow of energy can wash life and consciousness into the world. Compounding the trouble is the slippery notion of entropy, reasonably well defined for thermodynamic purposes in terms of heat and temperature, but devilishly hard to pin down as a measure of disorder. Physicists have trouble enough measuring the degree of order in water, forming crystalline structures in the transition to ice, energy bleeding away all the while. But thermodynamic entropy fails miserably as a measure of the changing degree of form and formlessness in the creature of amino acids, of microorganisms, of self-reproducing plants and animals, of complex information systems like the brain. Certainly, these evolving islands of order must obey the second law. The important laws, the creative laws, lie elsewhere. Nature forms patterns. Some are orderly in space but disorderly in time, others in time but disorderly in space. Some patterns are fractal, exhibiting structures self-similar in scale. Others give rise to steady states of oscillating ones. Pattern formation has become a branch of physics and of material science, allowing scientists to model the aggregation of particles into clusters, the fractured spread of electrical discharges, and the growth of crystal in ice and metal alloys. The dynamics seem so basic, shapes changing in space and time, yet only now are the tools available to understand them. It's a fair question now to ask a physicist, why are all snowflakes different? Ice crystals form in the turbulent air with a famous blending of symmetry and chance, the special beauty of sixfold indeterminacy. As water freezes, crystals send out tips. The tips grow, their boundaries become unstable, and new tips shoot out from the sides. Snowflakes obey mathematical laws of surprising subtlety, and it was impossible to predict precisely how fast a tip would grow, how narrow it would be, or how often it would branch. Generations of scientists sketched and catalogued formation as a classification matter for lack of a better approach. Growth of such tips, dendrites, is now known as a highly nonlinear, unstable free boundary problem, meaning that models need to track a complex, wiggly boundary as it changes dynamically. When solidification proceeds from outside to inside, as in an ice tray, the boundary generally remains stable and smooth, its speed controlled by the ability of the walls to draw away the heat. But when a crystal solidifies outward from an initial seed, as a snowflake does, grabbing water molecules while it falls through the moisture-laden air, the process becomes unstable. Any bit of boundary that gets out ahead of its neighbors gains an advantage in picking up new water molecules and therefore grows that much faster, the lightning rod effect. New branches form and then sub-branches. One difficulty was in deciding which of the many physical forces involved are important and which can safely be ignored. Most important, as scientists have long known, is the diffusion of the heat released when water freezes. But the physics of heat diffusion cannot completely explain the patterns researchers observe when they look at snowflakes under microscopes or grow them in the laboratory. Recently, scientists worked out a way to incorporate another process, surface tension. The heart of the new snowflake model is the essence of chaos, a delicate balance between forces of stability and forces of instability, a powerful interplay of forces on atomic scales and forces on everyday scales. Where heat diffusion tends to create instability, surface tension creates stability. The pull of surface tension makes a substance prefer smooth boundaries like the wall of a soap bubble. It costs energy to make surfaces that are rough. The balancing of these tendencies depends on the size of the crystal. While diffusion is mainly a large-scale macroscopic process, surface tension is strongest at the microscopic scales. Traditionally, because the surface tension effects are so small, researchers assumed that for practical purposes they could disregard them. Not so. The tiniest scales proved crucial. There, the surface effects proved infinitely sensitive to the molecular structure of a solidifying substance. In the case of ice, a natural molecular symmetry gives a built-in preference for 6 directions of growth. To their surprise, scientists found that the mixture of stability and instability manages to amplify this microscopic preference, creating the near fractal lacework that makes snowflakes. The mathematics came not from atmospheric scientists, but from theoretical physicists, along with metallurgists who had their own interest. In metals, the molecular symmetry is different, and so are the characteristic crystals which help determine an alloy's strength. But the mathematics are the same. The laws of pattern formation are universal. Sensitive dependence on initial conditions serves not to destroy, but create. As a growing snowflake falls to earth, typically floating in the wind for an hour or more, the choices made by the branching tips at any instant depend sensitively on such things as the temperature, the humidity, and the presence of impurities in the atmosphere. The 6 tips of a single snowflake, spreading within a millimeter space, feel the same temperatures, and because the laws of growth are purely deterministic, they maintain a near-perfect symmetry. But the nature of turbulent air is such that any pair of snowflakes will experience very different paths. The final flake records the history of all the changing weather conditions it's experienced, and the combinations may as well be infinite. Snowflakes are non-equilibrium phenomena. Physicists like to say that. They are products of imbalance in the flow of energy from one piece of nature to another. The flow turn a boundary into a tip, the tip into an array of branches, the array into a complex structure never before seen. As scientists have discovered such instability obeying the universal laws of chaos, they have succeeded in applying the same methods to a host of physical and chemical properties and problems, and inevitably They suspect that biology is next. In the back of their minds, as they look at computer simulations of dendrite growth, they see algae, cell walls, organisms budding and dividing. From microscopic particles to everyday complexity, many paths now seem open. In mathematical physics, the bifurcation theory of Feigenbaum and his colleagues advances in the United States and Europe. In the abstract reaches of theoretical physics, scientists probe other new issues, such as the unsettled question of quantum chaos. Does quantum mechanics admit the chaotic phenomena of classical mechanics? In astronomy, chaos experts use unexpected gravitational instabilities to explain the origin of meteorites, the seemingly inexplicable catapulting of asteroids from far beyond Mars. Scientists use the physics of dynamical systems to study the human immune system with its billions of components and its capacity for learning, memory, and pattern recognition, and they simultaneously study evolution, hoping to find universal mechanisms of adaptation. Those who make such models quickly see structures that replicate themselves, compete, and evolve by natural selection. Evolution is chaos with feedback, Joseph Ford said. The universe is randomness and dissipation, yes. But randomness with direction can produce surprising complexity. And as Lorenz discovered so long ago, dissipation is an agent of order. God plays dice with the universe is Ford's answer to Einstein's famous question. But they're loaded dice. And the main objective of physics now is to find by what rules were they loaded, and how can we use them for our own ends. Such ideas help drive the collective enterprise of science forward. Still, no philosophy, no proof, no experiment ever seems quite enough to sway the individual researchers for whom science must first and always provide a way of working. In some laboratories, the traditional ways falter. Normal science goes astray. As Kuhn puts it, a piece of equipment fails to meet expectations. The profession can no longer evade anomalies. For any one scientist, the ideas of chaos could not prevail until the method of chaos became a necessity. Every field had its own examples. In ecology, there was William M. Schaffer, who trained as the last student of Robert MacArthur, the dean of the field in the 50s and 60s. MacArthur built a conception of nature that gave a firm footing to the idea of natural balance. His models supposed that equilibriums would exist and the populations of plants and animals would remain close to them. To MacArthur, balance in nature had what could almost be called a moral quality. States of equilibrium in his models entailed the most efficient use of food resources, the least waste. Nature, if left alone, would be good. 2 decades later, MacArthur's last student found himself realizing that ecology based on a sense of equilibrium seems doomed to fail. The traditional models are betrayed by their linear bias. Nature is more complicated. Instead, he sees chaos both exhilarating and a bit threatening. Chaos may undermine ecology's most enduring assumptions, he tells his colleagues. What passes for fundamental concepts in ecology is as mist before the fury of the storm. In this case, a full, non-linear storm. Schaffer is using strange attractors to explore the epidemiology of childhood diseases such as measles and chickenpox. He's collected data, first from New York City and Baltimore, then from Aberdeen, Scotland, and all England and Wales. He's made a dynamical model resembling a damped-driven pendulum. The diseases are driven each year by the infectious spread among children returning to school and damped by natural resistance. Schaffer's model predicts strikingly different behavior for these diseases. Chickenpox should vary periodically. Measles should vary chaotically. As it happens, the data show exactly what Schaffer predicts. To a traditional epidemiologist, the yearly variations in measles seemed inexplicable, random and noisy. Schaffer, using the techniques of phase space reconstruction, shows that measles follow a strange attractor with a fractal dimension of about 2.5. Schaffer computed Lyapunov exponents and made Poincare maps. More to the point, Schaffer said, if you look at the pictures, it jumps out at you, and you say, my God, this is the same thing. Although the attractor is chaotic, some predictability becomes possible in light of the deterministic nature of the model. A year of high measles infection will be followed by a crash. After a year of medium infection, the level will change only slightly. A year of low infection produces the greatest unpredictability. Schaffer's model also predicted the consequences of damping the dynamics by mass inoculation programs, consequences that could not be predicted by standard epidemiology. On the collective scale and on the personal scale, the ideas of chaos advance in different ways and for different reasons. For Schaffer, as for many others, the transition from traditional science to chaos came unexpectedly. At first, he thought the mathematical ideas were unrealistic for the kinds of systems a practicing ecologist would study. These were one-dimensional maps, he thought. What bearing could they have on continuously changing systems? So a colleague said, read Lorenz. He wrote the reference on a slip of paper and never bothered to pursue it. Years later, Schaffer lived in the desert outside of Tucson, Arizona, and summers found him in the Santa Catalina Mountains just to the north, islands of chaparral, merely hot when the desert floor is roasting. Amid the thickets in June and July, after the spring blooming season and before the summer rain, Schaffer and his graduate students tracked bees and flowers of different species. This ecological system was easy to measure despite all its year-to-year variation. Schaffer counted the bees on every stalk, measured the pollen by draining flowers with pipettes, and analyzed the data mathematically. Bumblebees competed with honeybees, and honeybees competed with carpenter bees, and Schaffer made a convincing model to explain the fluctuations in population. By 1980, he knew that something was wrong. His model broke down. As it happened, the key player was a species that he'd overlooked, ants. Some colleagues suspected unusual winter weather, others unusual summer weather. Schaffer considered complicating his model by adding more variables, but he was deeply frustrated. Word was out among the graduate students that summer at 5,000 feet with Schaffer was hard at work, and then everything changed. He happened upon a preprint about chemical chaos in a complicated laboratory experiment, and he felt that the authors had experienced exactly his problem. The impossibility of monitoring dozens of fluctuating reaction products in a vessel matched that impossibility of monitoring dozens of species in the Arizona mountains. Yet they had succeeded where he had failed. He read about reconstructing phase space. He finally read Lorenz and others. The University of Arizona sponsored a lecture series on order in chaos. When an experimenter explained chemical chaos, displaying a transparency of a strange attractor, and said, "That's real data," a chill ran up Schaffer's spine. "All of a sudden, I knew that was my destiny," Schaffer said. He had a sabbatical year coming. He withdrew his application for National Science Foundation money and applied for a Guggenheim Fellowship. Up in the mountains, he knew the ants changed with the season. Bees hovered and darted in a dynamical buzz. Clouds skidded across the sky. He couldn't work the old way anymore. Copyright 1989 by Dove Books on Tape Incorporated.